Welcome, weary traveler of thought. As you find yourself in this quiet space, a gentle pause in the ceaseless rhythm of your day. Breathe softly now, letting the air fill you with a tranquil calm, and then release it, letting go of any lingering echoes of yesterday or tomorrow. Where are you in this moment? What time does your internal clock whisper to you? Does the world outside still hum with activity, or has it settled into a hushed stillness? Here, in this gentle sanctuary of sound and words, those questions are simply invitations for your mind to drift, to wander, to simply be. There is no need for answers here, no urgency to solve, no pressure to learn. This is not a lesson, nor is it a therapy session. Instead, think of it as a soft blanket woven from threads of curiosity and wonder, inviting you to simply recline, to close your eyes, and to let your thoughts meander through the grand, whispering concepts of the cosmos. Let us embark on a quiet journey together, not to seek firm conclusions, but to simply explore the delicate dance of scientific ideas that unfold within the infinite silence. As we begin this gentle drift, our thoughts might naturally turn to the vast, swirling tapestry of the night sky, a canvas painted with distant lights, and amongst those countless pinpricks of brilliance, there are some that hold a special, almost intimate place in our cosmic neighborhood. Perhaps you have heard their names whispered in hushed tones, or seen them referenced in the quiet corners of scientific documentaries. They are known collectively as Alpha Centauri, a name that carries a certain weight, a feeling of both proximity and profound distance. This triple star system, our closest celestial neighbors beyond our own sun, resides just over 4 light years away. 4 light years. It's a number, of course, a measure of cosmic scale. But if we allow our minds to linger on it for a moment, we can begin to appreciate its true, poetic meaning. Imagine, but if you will, a single beam of light born from the surface of our sun, or perhaps from the very star we are now considering, Alpha Centauri. This light, this tiny packet of energy, begins a journey, traveling at the fastest speed anything can possibly move through the universe. It rushes, ceaselessly, for an entire year, covering an unimaginable distance. That distance, that silent journey of light for 1 full year, is what we call a light year. And Alpha Centauri, our celestial next-door neighbor, is not just 1 light year away, nor 2, but just over 4 of these vast, luminous stretches. It's a distance so immense that if you were to journey there in the fastest spacecraft humanity has ever conceived, it would still take generations for your descendants to finally arrive. Generations. Think of the quiet passage of time, the stories that would unfold across such an expanse of years, all within the silent, unending voyage towards a point of light that we can almost, but not quite, touch. Yet, despite this profound, unbridgeable distance in human terms, Alpha Centauri is, cosmically speaking, right on our doorstep. It is the very closest star system to our solar system, an anchor in the vast, dark ocean of interstellar space. When we look up, or when we simply allow our minds to drift across the cosmic landscape, this system whispers to us of connection, of shared space, even if that space is grand beyond our immediate comprehension. It's a reminder that even in the seemingly infinite emptiness, there are always neighbors, always points of light calling to each other across the deep. This system is not a singular, solitary beacon, but rather a complex, delicate dance of 3 stars. There is Alpha Centauri A, sometimes known by its historical name, Rigel Kentaurus, a star that bears a remarkable resemblance to our own cherished sun, and then its companion, Alpha Centauri B, or Ptolemy, another star that mirrors our sun in many ways. Together, these two, Alpha Centauri A and B, form a captivating binary star system, Alpha Centauri AB, they are locked in an eternal waltz, circling a common center, a gravitational pivot point, with a grace that has unfolded for billions of years. Imagine the quiet grandeur of this cosmic ballet. Two suns orbiting each other, forever bound, forever moving in a slow, stately rhythm that completes one full revolution every 76 years. Almost 80 years for a single embrace in the vastness. It's a time scale that makes our human lives feel fleeting, yet within it, we can glimpse the enduring, patient mechanics of the universe. These two stars, Rigel, Centaurus, and Ptolemy, are not just distant lights, they are sun-like stars. They burn with a similar kind of warmth, a similar kind of light to our very own star. This similarity, this cosmic echo, is a whisper of familiarity in the alien expanse. It invites us to wonder if our sun nurtures life. Might theirs too? Perhaps in forms we can barely imagine, on worlds we have yet to truly see. The thought drifts, like a gentle cloud, across the landscape of our mind. For those of you fortunate enough to reside in the southern hemisphere, perhaps south of the 40th parallel, these celestial companions may even be visible to your unaided eye on a clear, dark night. You might look up, and there they would be, a faint, shimmering point of light, appearing to be a single star. Yet, beneath that tranquil glimmer lies the intricate duality of two suns, locked in their timeless embrace. To the naked eye, they would appear as one, a single unwavering diamond in the dark velvet. This phenomenon, this seeming simplicity masking a profound complexity, is a recurring theme in the universe, isn't it? A gentle reminder that what we perceive at first glance is often merely the surface of a deeper, more intricate reality. And for those who can see it, this single point of light would be the third brightest star in the night sky, behind only the dazzling brilliance of Sirius and the majestic glow of Canopus. Imagine the quiet satisfaction, the profound sense of connection, of looking up and seeing a star system that is, at once, a distant neighbor and a grand visible presence in our shared sky. The discovery of this binary Alpha Centauri system wasn't a sudden flash of insight, but a gradual unfolding of cosmic understanding. It was in the distant year of 1689 that this elegant pair, these two suns dancing together, first revealed their presence to human observation. But the universe, in its gentle wisdom, often keeps its deepest secrets close, unveiling them only when we are truly ready to perceive them. And so, for over 200 long years, the existence of the third star in this system, the silent, elusive companion, remained hidden, a secret held within the vast, shimmering fabric of space. 2 centuries passed, filled with human striving, scientific advancement, and countless nights spent gazing up at the enigmatic heavens, before the final piece of this cosmic puzzle began to reveal itself. The moment of revelation of that quiet, profound discovery finally arrived in the year 1915. Imagine the quiet dedication of the astronomers of that era, working with instruments that, to our modern eyes, might seem rudimentary, yet possessed a profound power in the hands of those who truly understood the language of the stars. It was in this year that fortune, or perhaps the universe's gentle timing, smiled upon a Scottish astronomer named Robert Innes. He was a dedicated soul, working as the director of the Union Observatory in Johannesburg, South Africa, a place where the southern skies opened up in all their brilliant glory. His work was meticulous, a patient, almost meditative process of comparison. He would pore over photographic plates, comparing them with the help of a blink comparator. Imagine this device, 2 images, taken at different times, viewed through a rapid, rhythmic shift, like the blinking of an eye. And as Innes patiently blinked, comparing one image to another. A subtle, almost imperceptible shift caught his discerning eye. A faint star, a mere whisper of light, seemed to have moved. Not much, just a tiny, almost shy displacement in the 5 years that separated the two photographs he was scrutinizing. 5 years. Think of the patience, the meticulous attention to detail required to notice such a minute change over such a span of time. What made this tiny movement so profoundly significant was its similarity to the movement of the very stars he was diligently observing, the Alpha Centauri binary system itself. A flicker of possibility, a gentle stirring of curiosity, must have bloomed in Innes's mind. Could this new, faint star, this quiet wanderer, be a part of the same grand system? Could it be a hidden sibling to Rigel Kentaurus and Ptolemy? The thought, once planted, began to gently take root, nudging him towards further, deeper investigation. He delved, patiently and meticulously, into more observations, more calculations, more whispered conversations with the data, and slowly, painstakingly, the truth began to emerge. His investigations led him to a remarkable conclusion, one that would quietly reshape our understanding of our immediate cosmic neighborhood. This newly found star, this faint, moving light, was not only a part of the Alpha Centauri system, but it was also, paradoxically, even closer to our sun than its two brighter siblings, a finding so startling, so counterintuitive at first glance, yet one that, once unveiled, was quickly and reassuringly confirmed by his contemporaries, the other astronomers of his time, who, in their own patient observations, also saw the truth of his discovery. This was a moment of profound, gentle paradox. For this newfound star, this quiet, closest neighbor, simultaneously became both the closest known star to humanity and the dimmest known star at the time. Imagine the quiet astonishment, the subtle shift in perspective that such a discovery would bring. The nearest point of light, yet barely visible, a whisper in the cosmic dark. It's a beautiful illustration of how the universe often surprises us, holding its most profound secrets not in the loudest, brightest displays, but sometimes in the softest, most unassuming corners. The story of Proxima Centauri, as this quiet, closest star would come to be known, had only just begun to unfold its gentle, intriguing layers. Its very existence, a testament to the patient, unwavering curiosity that drives our exploration of the vast, silent cosmos. And as we ponder this quiet beginning, we can feel the gentle pull of its mystery, inviting us to linger, to wonder, and to simply be present with the unfolding narrative of the stars. The universe, it seems, delights in presenting us with unexpected gifts, wrapped in layers of paradox and quiet revelation, and the surprises held within the embrace of Proxima Centauri, our newly discovered, dimmest yet closest stellar neighbor, were far from over. Decades after its initial, gentle unveiling, another profound truth about this star began to glimmer into view. It was in the year 1951, a time when our understanding of stars, though growing, was still in its formative years, that an American astronomer named Harlow Shapley made a truly remarkable discovery. Shapley, a name that resonates with giants of astronomical thought, found that Proxima Centauri was not just a quiet, unassuming red dwarf, but something far more dynamic, far more alive. He discovered it was a flare star. Now, what does it mean for a star to be a flare star? Imagine our own sun, a familiar, comforting presence in our sky. It has its moments of activity. Of course, its sunspots and occasional solar flares, gentle ripples on its fiery surface. But imagine a star whose surface is far more volatile, far more prone to sudden, dramatic outbursts of energy. That is a flare star. These are stars that randomly experience drastic, sometimes explosive, changes in brightness and energy emissions. It's as if the star, in its quiet, constant burning, suddenly lets out a powerful, radiant sigh, a burst of magnetic energy that sends its light skyrocketing for a brief, intense period. And Shapley's discovery was even more astonishing. Not only was Proxima Centauri a flare star, but at that time, it was recognized as the most active flare star known. Think of the quiet irony: the dimmest, closest star was also, unexpectedly, one of the most energetically volatile, a tiny, unassuming cosmic firecracker. This revelation, this understanding of Proxima Centauri's vibrant, active nature, set the stage for decades of intense, quiet study. Over the last 70 years, this little red dwarf, once merely a faint dot noticed by a blink comparator, has become a star of fervent interest, a subject of heated, if you'll pardon the gentle pun, investigation. Scientists, drawn by its enigmatic activity and its tantalizing proximity, have turned their instruments, their calculations, and their deepest curiosities towards it. And as we allow our minds to drift into the present moment, we can see why this fascination has only intensified. With the recent exciting discoveries of Earth-like exoplanets quietly orbiting Proxima Centauri, the interest in this small, vibrant star is not just intensifying, it's almost certainly reaching new, profound heights. The thought of potential worlds, nestled in its energetic embrace, beckons us with silent questions about life, about cosmic destiny, about our place in this vast unfolding story. But let us not get ahead of ourselves, dear listener, for the cosmos, in its infinite wisdom, unfolds its secrets with a graceful slowness. Before we place such grand expectations upon this star, before we imagine distant journeys to its potential worlds, let us take a moment, a quiet pause, to simply get to know this star a little better, to understand its fundamental nature. It is, after all, our closest stellar neighbor, and like any good neighbor, it deserves our gentle, patient attention. So, let us begin with its cosmic address. Proxima Centauri resides at a distance of 4.24 light-years from us. This makes it ever so slightly closer to us than its two binary siblings, Alpha Centauri AB, a tiny, subtle difference in the grand scheme of the universe, yet significant enough to make it the very closest star to our solar system. Imagine that, a star, a sun in its own right, just a tiny fraction of a light-year nearer than its companions, holding the record for ultimate stellar proximity to our home. Now, let us consider its fundamental identity. Proxima Centauri is what astronomers refer to as a main-sequence red dwarf star. This classification tells us a great deal about its nature. Unlike our Sun, which is a yellow dwarf, red dwarfs are typically much smaller, cooler, and far less luminous. They are the quiet, unassuming, yet incredibly common denizens of the galaxy. Proxima Centauri, in particular, has an estimated mass of only 12.2% that of our Sun, and a diameter that is a mere 15% of our Sun's vast expanse. Picture that, a star so much smaller, so much more compact than the radiant orb that warms our planet. It's a testament to the incredible diversity of stars that populate our universe, each burning in its own unique way. Yet, despite its diminutive size, Proxima Centauri holds another fascinating secret of density. Due to its low mass, the interior of this star is almost entirely convective. Imagine, if you will, a giant, slow-boiling pot of cosmic plasma, constantly churning and bubbling, carrying energy from its core all the way to its surface. this continuous, profound churning, this total convection, is what generates a powerful magnetic field around the star. And it is this intricate, dynamic magnetic field that in turn leads to the sporadic, sometimes violent, release of magnetic energy in the form of those very flares that Harlow Shapley discovered so many decades ago. The quiet churn beneath the surface manifesting as brilliant, fleeting outbursts of light and energy on its exterior. As a direct consequence of this internal, convective ballet, Proxima Centauri randomly experiences those drastic changes in brightness and energy emissions we spoke of. One moment, a quiet, steady glow, and the next, a sudden, powerful surge of light, like a cosmic gasp. It's a dynamic, unpredictable nature that stands in gentle contrast to the relative stability of our own sun. Consider a recent striking example of this stellar temperament. On the 6th of May, 2019, a flare event on Proxima Centauri was observed, and it was a truly monumental one, recorded as being the brightest ever witnessed from this star. Imagine the sheer outpouring of energy, a cosmic exclamation mark in the silent expanse. These flares, these powerful bursts of magnetic energy, release radiation across the entire electromagnetic spectrum, including powerful X-rays. Think for a moment about the implications of such an event for any potential world orbiting this star. To help you gently grasp the sheer scale of Proxima Centauri's solar activity, consider this quiet comparison. Its baseline X-ray luminosity, the steady, constant emission of X-rays, even when it's not flaring, is roughly equivalent to that of our sun. Now, let that sink in for a moment. Our sun is a much larger, much hotter star, yet this tiny red dwarf, Proxima Centauri, in its quiet, everyday existence, emits X-rays at a comparable level. But then, when a flare erupts, that level of X-ray emission can increase by an astonishing 2 orders of magnitude. Imagine the gentle, continuous hum of a quiet machine suddenly roaring to life with a sound 100 times louder. That is the kind of dramatic, energetic transformation that occurs on the surface of Proxima Centauri during one of its powerful flares. And it's not just the intensity of these flares that is remarkable. Proxima Centauri also boasts a higher frequency of solar activity compared to our sun. It's estimated that a remarkable 88% of the star's surface is active at any given time. Compare this to our sun, which even at the peak of its solar cycle, displays a far more modest level of surface activity. This pervasive, almost continuous activity on Proxima Centauri's surface paints a picture of a star constantly simmering with magnetic energy, frequently bubbling over with intense, radiating bursts. Now, before you begin to imagine Proxima Centauri as some terrifying, fiery ball of cosmic fury, let us gently pause and remember a crucial point. We are, in essence, comparing apples and oranges here. Our sun is not a red dwarf. It belongs to a different stellar class altogether. So, a direct, one-to-one comparison of their activity levels can be misleading without proper context. In fact, when compared to other red dwarfs, its own kind, Proxima Centauri is actually considered to have a low activity level. This gentle distinction reminds us that the universe is filled with incredible diversity, and each type of star, each cosmic entity, operates within its own unique set of parameters. What might seem extreme to us, accustomed to the gentle stability of our yellow dwarf sun, is simply the quiet, everyday rhythm for a red dwarf like Proxima Centauri. And here lies perhaps one of the most profound and humbling differences between Proxima Centauri and our sun, a difference that speaks to the very fabric of cosmic time. Scientists estimate that our sun, in its magnificent burning lifetime, will only consume about 10% of its hydrogen fuel before gently burning out, transforming into a red giant, and eventually a white dwarf. It is a long, glorious journey, but one with a finite conclusion. Proxima Centauri, however, is a star of an entirely different, almost immeasurable, endurance, due to its unique convective internal structure and its much slower rate of burning. It is predicted to use up almost all of its fuel before leaving the main sequence, and the timescale for this quiet, patient consumption, a staggering 4 trillion years. 4 trillion years. Let that number, that immense, almost incomprehensible span of cosmic time, gently wash over you. It is a duration so vast that, by then, our Earth, our Sun, and indeed our entire solar system will have long since faded from existence, becoming mere whispers in the cosmic winds. Proxima Centauri is a testament to the universe's capacity for incredible, enduring patience, a quiet, flickering flame that will outlast almost everything we know. Now, let us return to the larger family portrait of the Alpha Centauri system and gently place Proxima Centauri back into its context. We know that Alpha Centauri AB, the graceful dancing binary pair, resides a considerable distance from Proxima Centauri. To be precise, Alpha Centauri AB is 0.13 light years, or a staggering 2 trillion kilometers away from Proxima Centauri. This is an immense gulf, a vast expanse of empty space that separates the two components of what we call a single stellar system. You might, quite naturally, be wondering if Proxima Centauri is so far removed from its companion stars, why is it considered part of the same stellar system at all? Why isn't it simply a rogue star, drifting independently through the cosmic dark? The answer lies in the subtle yet incredibly powerful language of gravity. We possess a wealth of data, painstakingly collected and carefully analyzed, that clearly demonstrates that Proxima Centauri is gravitationally bound to the Alpha Centauri AB binary star. Imagine a silent, invisible thread stretching across those 2 trillion kilometers, gently but firmly connecting Proxima Centauri to the two suns that dance far away. This gravitational embrace, this unseen tether, is what definitively makes it a part of the grander Alpha Centauri stellar system. Their relationship is not one of close proximity in space, but of enduring connection through the fundamental force of the universe. And what a relationship it is. Proxima Centauri gently orbits its two brighter siblings, not in a tight, fast dance, but in a vast, leisurely, almost glacial cycle. Its orbital period around Alpha Centauri AB is an astonishing 550,000 years. Imagine the quiet passage of 500,000 years for a single revolution around its distant companions. It's a timescale that truly dwarfs our human experience, a testament to the patient, unhurried rhythm of the cosmos. This intricate, extended orbit is a cosmic ballet performed in slow motion, a silent testament to the enduring power of gravitational attraction across truly immense distances. However, how Proxima Centauri ended up in this unique orbital situation, a distant yet gravitationally bound third member of a binary system, is still a matter of gentle speculation, a quiet mystery that scientists continue to ponder. The universe, in its intricate complexity, often leaves us with fascinating puzzles, inviting us to explore the different possibilities that might have led to the current cosmic arrangement. There appear to be two main scenarios that whisper through the halls of scientific thought, each painting a slightly different picture of Proxima Centauri's origins. The first scenario suggests a shared birth, a common beginning. Perhaps Proxima Centauri was bound to the Alpha Centauri system during its very formation. Imagine a vast, swirling cloud of gas and dust, gradually collapsing under its own gravity, giving birth to multiple stars simultaneously. In this gentle, chaotic nursery, Proxima Centauri, might have simply formed alongside its two larger siblings, right from the very beginning, intrinsically linked by their shared cosmic parentage. If this indeed were the case, it would imply that these three stars likely share the same elemental composition, having been forged from the same primeval cosmic material. A beautiful thought. Isn't it three stars, born from the same cosmic dust, destined to dance together for eons? The second scenario paints a picture of a chance encounter, a gentle gravitational embrace from afar. It posits that Proxima Centauri was captured by the binary star's gravity during an encounter sometime after its own formation. Imagine Proxima Centauri as a solitary wanderer, drifting through the vastness of space, perhaps born from a different, distant cloud. As it gently approached the powerful gravitational pull of the Alpha Centauri AB binary, it might have been subtly drawn in, caught in their invisible, magnetic field of influence. This encounter, this slow gravitational tug, could have initially led to a highly eccentric orbit, a wild, elongated path that gradually, over immense spans of cosmic time, was stabilized by the gentle, pervasive influence of the galactic tide and further, quieter stellar encounters. The universe in this scenario is a place of grand, gravitational happenstance where paths cross and new, enduring connections are subtly forged across the deep. Regardless of which gentle cosmic path led Proxima Centauri into its current triplet configuration, the calculations of astronomers suggest a future separation, a gradual unbinding that will occur billions of years from now. It is predicted that in about 3.5 billion years, Proxima Centauri will gently break free from the gravitational embrace of its companions. This will happen as Alpha Centauri AB continues its own slow evolution, subtly losing mass over its incredibly long lifetime. As the mass gently diminishes, the gravitational grip weakens, and Proxima Centauri will slowly, gracefully, unbind from the system, becoming a truly independent wanderer. And the binary star system itself, Alpha Centauri AB, is also predicted to undergo its own profound transformation, a final, quiet divergence. In about 12 billion years, after their long, intricate dance, they too are predicted to dissociate, to gently part ways, each transforming into a white dwarf. These stellar remnants, the quiet ghosts of once brilliant suns, will then forge independent and steadily diverging paths through the cosmic void. It's a reminder of the transient nature of even the most enduring cosmic relationships, a gentle whisper that all things, even stars, must eventually change and move on. As our closest stellar neighbors, we certainly know a considerable amount about Alpha Centauri AB, their sizes, their orbits, their gentle, enduring dance. However, their story, their intricate details, are threads best explored in another quiet conversation, another journey into the depths of cosmic understanding. For now, our gentle gaze, our profound curiosity, remains fixed squarely on Proxima Centauri. It is this small, vibrant red dwarf that holds the tantalizing, whispering secrets of potential worlds, worlds that beckon us with silent questions about the possibility of life beyond our own blue planet. And it is to these potential worlds, these quiet whispers of distant habitability, that our thoughts now gently turn, inviting us to delve deeper into the ongoing, patient search for exoplanets around our closest stellar neighbor. The search for exoplanets around Proxima Centauri has been a patient, often quiet, endeavor, unfolding since the mid-2000s. For many years, the universe seemed to hold its secrets close, offering little immediate reward for this diligent quest. Yet, researchers, driven by an unyielding curiosity and a profound sense of scientific purpose, were simply not willing to give up. Their persistence was fueled by a deep understanding of cosmic possibilities. Not only was this star, Proxima Centauri, our closest stellar neighbor, holding the promise of accessible study, but it was also a red dwarf. And within the vast, whispering statistical landscapes of the cosmos, there is a fascinating truth about red dwarfs. An estimated 20 to 40% of them are believed to harbor planets orbiting within their habitable zones. Imagine the quiet hope, the profound potential embedded in that statistic. A significant fraction of these tiny, enduring stars, so common throughout the galaxy, might just be nurturing worlds where the conditions for liquid water, and perhaps even life, could exist. This silent promise, this gentle beckoning, sustained the patient search. And indeed, that patience, that unwavering dedication gently began to yield its profound rewards. Observations conducted at the prestigious European Southern Observatory in Chile, a place where the universe truly opens up to our gaze, began to identify subtle anomalies in the behavior of Proxima Centauri. These were not the dramatic, fiery flares we have discussed, nor could they be easily explained by other familiar solar activities. Instead, the data presented a quiet, persistent whisper, suggesting something else at play, something unseen. The patterns seemed to indicate ever so gently that there might be a planet, a hidden world, quietly orbiting this unassuming red dwarf. Imagine the thrill, the silent excitement that must have rippled through the scientific community as these first tantalizing hints began to emerge from the vastness of space. To confirm this whisper, to truly unveil the suspected planet, a coordinated global effort was gently launched in January 2016. It was named, quite evocatively, the Pale Red Dot Campaign. Think of the imagery: a tiny, faint red star, barely visible, yet holding the potential for a new, pale, red dot of a world within its embrace. This campaign brought together multidisciplinary scientists from across the globe, uniting their expertise and leveraging ground-based telescopes around the world in a concerted effort. Their mission was clear: to search, to observe, to meticulously analyze, and to see if this elusive, suspected planet could finally be identified with enough certainty to confirm its quiet existence. And so, in August of that same year, after months of patient observation and careful analysis, the universe offered another one of its profound revelations. The discovery of the exoplanet Proxima Centauri b was officially announced, a moment that sent ripples of quiet excitement and profound wonder throughout the world. Here, nestled in the embrace of our closest stellar neighbor, was a world, an alien landscape, now brought into the gentle light of human understanding. Let us now quietly consider what we know about this newfound world. This Proxima b, it is believed to be at least 1.07 times larger than Earth, a subtle difference that makes it remarkably similar in size to our own home planet and its orbit. It sits incredibly close to Proxima Centauri, about 20 times closer to its star than we are to our sun. Imagine the intense intimacy of that orbital dance, a world so tightly bound to its star. This close proximity means that Proxima b completes an orbit around its star in a mere 11.2 Earth days. Think of the rapid passage of its years, a blur of seasons on a world so different from our own. Now, here is where the gentle paradox of habitability begins to unfold. Even though Proxima b resides squarely within Proxima Centauri's habitable zone, that elusive, theoretical region where temperatures might allow for liquid water to exist on a planet's surface that does not, by any means, guarantee it could sustain life as we know it, the universe, in its intricate design, has many more factors at play, many more subtle conditions that determine true habitability than simply the presence of liquid water. It is a nuanced, delicate balance of cosmic forces and environmental conditions. For one, Consider the relentless assault of intense solar activity. Proxima Centauri, as we have learned, is a flare star, prone to powerful, sudden outbursts of energy. This means that Proxima b, orbiting so intimately close to its star, would be constantly bombarded with 10 to 60 times the amount of UV and X-ray radiation that we receive here on Earth. Imagine the sheer intensity of that cosmic shower, a relentless torrent of high-energy particles. To even contemplate a journey there, to imagine setting foot on such a world, we would, perhaps, need to develop a cosmic sunscreen with an unimaginable SPF 3000 to make the journey, and any attempt at life there truly worthwhile. The thought itself is a quiet challenge, isn't it? Another critical factor to gently ponder is the very survival of an atmosphere under such punishing conditions. As far as our current understanding reaches, an atmosphere is utterly vital for the maintenance of a water-friendly surface pressure, for protection from dangerous space weather, and for the delicate regulation of a planetary climate. Imagine the Earth's protective blanket, tirelessly shielding us from the harshness of space. The relentless radiation that Proxima b is exposed to might be enough, over vast stretches of cosmic time, to strip away the key components of an atmosphere, leaving the planet exposed and vulnerable, a world without its atmospheric embrace, a canvas utterly barren to the cosmic winds. Frustratingly, our knowledge of Proxima b, this closest of exoplanets, remains largely veiled in mystery beyond its distance from its star and its remarkably short orbital period. The intricate details of its nature, the very essence of its being, remain elusive, hidden from our direct gaze. It is considered unlikely to harbor any moons, primarily due to the inherent instability of their orbits over larger timescales in such a tightly bound system. The gravitational complexities would simply make it too challenging for a moon to maintain a stable, long-term embrace. However, a significant, perhaps even unsettling thought about Proxima b is that the planet itself is widely believed to be tidally locked to its star. We gently touched upon this concept in a previous conversation, and its implications for potential habitability are profound, and perhaps not at all promising. Imagine a world where the same side always faces its star, forever bathed in perpetual daylight, while the opposite side is forever plunged into eternal darkness. There is no gentle rotation, no rhythmic dance of day and night, only an unwavering, unchanging exposure. This cosmic lock, a result of powerful gravitational forces, paints a picture of extreme contrasts. Such a tidally locked world would likely have developed under conditions extremely different from those that nurtured our beloved Earth. If we assume, for a moment, that Proxima b formed at its current intimate distance from its star, it would have gone through a much faster evolution, perhaps experiencing stronger impacts from debris in its early history and, crucially, forming with far less water. Imagine a rapid, tumultuous birth, a stark contrast to the more temperate, hydrated origins of our home. Yet, there is some quiet debate, some gentle uncertainty, even about its formation location. Some scientists, with their keen insights, propose that the amount of material available in the protoplanetary disk, the swirling cloud of gas and dust from which planets are born, would have been insufficient for Proxima b to form at its current close distance from the star. It is, they suggest, more likely that the planet formed much farther away, in the cooler, richer outer reaches of its stellar system, and then, slowly, gracefully, drifted into its current orbit around Proxima Centauri. Imagine a long, slow migration, a journey from the outer darkness into the fiery, intimate embrace of its sun. This idea, this gentle suggestion of a wandering past, only adds to the enigmatic allure of Proxima b. As for what the actual surface of this planet might look like, We are left with pure, unadulterated speculation, a canvas for our wilder imaginings. Theories whisper in the quiet corners of scientific thought, ranging from a planet entirely covered in ice, a frozen, desolate realm, to one adorned with planet-wide oceans, much like our own vibrant Earth. Though, if the planet is indeed tidally locked, such Earth-like oceans might be unlikely, as the extreme temperature differences would surely create profound atmospheric and hydrological challenges. Alternatively, it could be a water-free world, a landscape of dry, parched land, or perhaps hiding a subsurface ocean, much like Europa, one of Jupiter's intriguing moons, rumored to harbor liquid water beneath its icy shell. In short, and with a gentle sigh of admission, we simply have no idea. We haven't directly imaged the planet yet, haven't seen its face, and so we must patiently wait for the first flybys, the future journeys of our intrepid probes, to get a better, more tangible understanding of this veiled world. And when that day comes, when those first distant images flicker back to us, I have a quiet feeling it will be just as earth-shattering, just as profoundly impactful as the legendary voyages of the Voyager missions which graced our outer solar system decades ago. But more on those grand future explorations and the gentle whispers of interplanetary travel a little later. The universe, in its intricate dance, often reveals its secrets slowly, patiently, sometimes with years or even decades, passing between the soft unveiling of one truth and the next. And so it was that, a mere 6 years after the initial, groundbreaking discovery of Proxima b, the news of another world, Proxima d, gently swept through global headlines, sending ripples of quiet excitement across the scientific community and beyond. The first subtle signs of this new planet emerged in 2020, a mere whisper in the vast cosmic data, a weak, almost imperceptible signal, oscillating with a period of 5.15 days, was detected in the meticulous radial velocity data. This data, a sensitive measurement of the tiny wobble in a star caused by the gravitational tug of an orbiting planet, was being carefully scrutinized during a study focused on refining the mass of Proxima b. Imagine the painstaking precision required to discern such a faint, almost shy, signal amidst the background hum of cosmic noise. It was a testament to the incredible sensitivity of our instruments and the unwavering dedication of the scientists who analyzed their output. Following this initial tantalizing hint, more patient data collection and even more rigorous analysis were undertaken. The universe, it seems, always demands thoroughness before it fully unveils its hidden gems. And so, in February 2022, after careful verification and robust confirmation, scientists proudly announced the discovery of Proxima d, a new world, a new tiny dot of existence, added to our ever-growing map of the cosmos. So, what do we know so far about this recently unveiled world, this Proxima d? It is classified as a sub-Earth planet, meaning it is smaller than our own home planet. Its estimated mass is remarkably light, at least 25% the mass of Earth. Imagine a world so ethereal, so delicate, compared to our own solid globe. Its orbit is even more intimate than Proxima b's, embracing its star every 5.1 days. Think of the lightning-fast passage of its years, a fleeting cosmic spin around its central sun, sitting at an incredibly close distance of 4.3 million kilometers from Proxima Centauri. Proxima d orbits far too intimately to possess a habitable equilibrium temperature. Its surface temperature would be driven up to a scorching 87 degrees, a heat that would render any liquid water impossible and certainly inhospitable for life as we know it. Like its sibling, Proxima b, it is also highly probable that Proxima d is tidally locked to its star. enduring the same extreme contrasts of perpetual day and eternal night. And, due to its close proximity and Proxima Centauri's active nature, it would undoubtedly be pelted with such a deluge of radiation that the chances of finding life there, in any form, are exceedingly slim. A beautiful world, perhaps, but one utterly unforgiving to our familiar forms of existence. Yet, despite these harsh realities regarding habitability, Proxima d holds a profound promise in another realm, entirely the realm of technological achievement and scientific ingenuity. This tiny, elusive planet is the lightest planet to ever be detected with the radial velocity method. Consider the challenge, since the planet itself is far too small and too close to its bright star to be seen directly with our telescopes. Scientists must rely on a characteristic, almost imperceptible, wobble in the movement of the star itself. This minute oscillation, this tiny dance, is the telltale sign that indicates the potential presence of an orbiting planet, its gravitational tug subtly pulling on its star. The more massive the planet, the more obvious, the more pronounced that wobble will be. But in the case of Proxima d, the wobble it induced in its star was practically imperceptible, a mere tremor in the grand cosmic rhythm. To me, the fact that we, with our ingenuity and our ever-advancing technology, were able to catch such a faint wobble, and then, with enough certainty, to demonstrate that it was indeed caused by a planet, is a technological milestone truly worth celebrating. It speaks to the incredible precision, the silent dedication, and the relentless pursuit of knowledge that defines human scientific endeavor. It's a testament to our capacity to discern the most subtle whispers from the universe, to find profound meaning in the most minute of cosmic shifts, a quiet triumph in the ongoing, beautiful story of astronomical discovery. However, if only the world of astronomy were so consistently straightforward, a clear path of breakthroughs and celebrations. Alas, where there is profound advancement and joyous discovery on one hand, there is often the quiet shadow of bleak uncertainty on the other, and that, dear listener, is precisely where you will find the controversial exoplanet Proxima c. Its story is woven with threads of tantalizing hints and lingering doubt, a testament to the complex, often challenging, nature of pushing the boundaries of human knowledge. Initially detected in 2019, Proxima c, like its more firmly established siblings, was first glimpsed using the very same radial velocity method that so triumphantly uncovered Proxima d. The subtle wobble in Proxima Centauri's light, this time with a much longer period, hinted at another companion, and for a brief, hopeful period, its existence seemed to be gently confirmed in 2020, bolstered by corroborating data from Hubble astrometry. Astrometry, the precise measurement of star positions, offered what seemed to be a secondary, independent verification of this elusive planet's presence. Imagine the quiet satisfaction, the growing confidence, as two different observational methods seem to whisper the same planetary secret. However, the universe, it seems, always has another twist, another layer of complexity to reveal. In 2022, another dedicated team of scientists, meticulously re-examining the data, gently challenged the initial radial velocity data that had led to the alleged discovery of Proxima c. Their argument was subtle, yet potent. They claimed that the anomalies, the faint wobbles that had been attributed to a planet, could instead have been associated with small, unaccounted systematic errors in the data extraction method. Essentially, they proposed a calibration issue, a subtle glitch in the way the raw data was being processed, rather than the undeniable tug of a distant world. It's a reminder that even in the most precise scientific endeavors, the human element, the subtle nuances of instrumentation and interpretation, can introduce layers of uncertainty. The trouble, the source of this profound uncertainty, arises from a crucial difference between Proxima C and its more confirmed sibling, Proxima D. Unlike Proxima D, which orbits incredibly close to its star, creating a relatively strong, if minute, wobble, the data for the alleged exoplanet Proxima C places it very far away from its star. Its estimated orbit is a vast 928 days, almost 5.5 Earth years, a truly extended journey around its parent sun. And here lies the core of the skepticism. There is simply no similar example of a wobble detection of a planet with such a low amplitude, meaning it barely tugs on its star at such a long orbital period. It's an unprecedented claim, pushing the very boundaries of what our current methods can reliably discern. Does this necessarily mean Proxima C is an illusion, a phantom planet born from data noise? Not definitively, no. As Paul Robertson, a respected astronomer at the University of California, Irvine, gently notes, that doesn't necessarily mean it's wrong, but it's going to require some confirmation from additional observations. His words echo the patient, cautious nature of true scientific inquiry. The universe, it seems, demands overwhelming evidence when we push into truly new and challenging territories. So, if Proxima C does indeed exist, it will undoubtedly take a bit more data, more patient observation, and perhaps new, more refined techniques to fully convince the reluctant skeptics within the scientific community. The burden of proof in this quiet cosmic court rests heavily on the shoulders of those who propose its existence. But then, if it does not exist, if Proxima C turns out to be merely a whisper of noise rather than the firm declaration of a world, then it remains profoundly unclear why the Hubble astrometric data was able to corroborate and confirm a planetary signature. That, too, would be a mystery, a new puzzle for astronomers to unravel. The universe, in its gentle, perplexing way, often gives us more questions than answers. And so, with a quiet acceptance of uncertainty, I guess we'll simply have to wait and see what future studies, what future whispers from the cosmos finally reveal. The story of Proxima C, it seems, is still very much in the making, a delicate thread awaiting its final definitive weave into the grand tapestry of our cosmic understanding. With the recent, captivating discovery of Proxima b and the remarkably close proximity of Proxima Centauri to our own solar system, it becomes, quite naturally, a perfect candidate for a future flyby mission. Imagine the gentle hum of a spacecraft, bravely venturing into the deep, heading towards that faint red beacon, a journey not just of distance, but of profound scientific and perhaps even philosophical discovery. The very thought ignites a quiet spark of wonder within us, doesn't it? However, the path to reaching our neighboring star system is not one of swift passage, but of immense, patient endurance, using conventional propulsion technologies, the kind that have gently carried our probes to the outer reaches of our own solar system. Such a trip to Alpha Centauri would demand thousands of years. Thousands of years. Let that immense span of time settle softly in your mind. It's a duration that stretches far beyond the brief flicker of a human lifetime, a journey that would require generations of quiet, unwavering commitment. But humanity, in its boundless curiosity and relentless ingenuity, does not easily concede to such daunting temporal barriers. Newer, more imaginative techniques, like the ethereal solar sails or the powerful controlled bursts of nuclear propulsion, hold a tantalizing promise. These advanced concepts whisper of a future where such a journey might just be possible within a single human lifetime. Imagine the profound shift in perspective, the very fabric of possibility stretching to accommodate such a grand endeavor. These ideas, These audacious dreams were the quiet genesis of Project Breakthrough Starshot. This initiative, spearheaded by the visionary investor and physicist Yuri Milner, is not merely a fanciful dream, but a bold, ambitious plan. Its ultimate aim is to reach the Alpha Centauri system within the first half of the 21st century. Think of the proximity of that timeline. The very near future potentially holding the key to interstellar travel. The core idea behind Breakthrough Starshot is to conduct a flyby mission of unprecedented scale and ingenuity by dispatching a fleet of tiny microprobes. Imagine these probes weighing just a few grams, perhaps no heavier than a feather, yet packed with an astonishing array of advanced technology, and their speed, a truly mind-boggling 15 to 20% the speed of light. Let that number, that incredible fraction of the ultimate cosmic speed limit, truly resonate within you. It is a speed that utterly dwarfs anything humanity has ever achieved in space travel, a silent whisper of a new era of exploration. And the architects of this grand vision believe, with quiet confidence, that they could achieve this remarkable feat as early as 2036. If this ambitious timeline holds true, these nimble microprobes would reach Alpha Centauri in a mere 20 years of silent, ceaseless flight. And then, after that initial, breathtaking flyby, the first invaluable data, the quiet whispers from our neighboring star system, would begin to reach us here on Earth, approximately 4 years later. Imagine the anticipation, the collective holding of breath, as humanity awaits the first tangible reports from a star system beyond our own, following that initial, momentous flyby. The mission envisions an even deeper exploration. These tiny probes, having completed their primary objective, would then possibly venture further, drifting gently towards the exoplanets themselves. Their mission to meticulously collect data on the atmospheric compositions of these alien worlds, searching for the subtle clues, the chemical fingerprints that might hint at the presence of life, or at least the conditions suitable for it. This endeavor echoes the profound, transformative work of the legendary Voyager missions, which, decades ago, provided humanity with its first intimate glances at the majestic, gas-shrouded worlds of our own outer solar system. A new generation of Voyagers, perhaps, but on an interstellar scale. The entire team behind Breakthrough Starshot is pinning their deepest hopes on a revolutionary piece of technology, one that is yet to be fully developed, a device they call the Star Chip. Imagine this, a microelectronic, gram-scale wafer, no bigger than a postage stamp, yet astonishingly capable. This tiny marvel would essentially constitute a fully functional space probe, carrying within its minuscule confines cameras to capture distant light, photon thrusters to gently guide its path, a power supply to sustain its journey, and all the necessary equipment for navigation and communication across the vast, silent interstellar void. It's a concept that pushes the very boundaries of miniaturization and engineering, a testament to the idea that sometimes the grandest ambitions can be realized through the smallest, most refined creations. This audacious concept is, in part, gently inspired by Moore's law, a principle that, though originally applied to computer processing power, resonates deeply with the spirit of accelerating technological progress. Moore's law states that the speed and capability of computers can be expected to double every 2 years, a relentless march of innovation. Breakthrough Starshot extends this idea to the very realm of space exploration, envisioning a future where our technological prowess allows us to build such incredibly compact and powerful interstellar explorers, bold and ambitious though it may be. This plan is certainly not without its formidable challenges, its quiet whispers of immense difficulty. The team proposes to power these tiny microprobes with an astounding 100 gigawatts of Earth-based lasers. Imagine the sheer focused intensity of that energy, it's the equivalent of the total electrical output of 100 large nuclear power plants, all concentrated onto probes that are mere centimeters wide. The technological hurdle of generating, focusing, and transmitting such an immense amount of power across vast distances with pinpoint accuracy is truly monumental, a silent testament to the scale of their ambition. Furthermore, every single component of these minuscule probes must be meticulously built to withstand the most extreme and unforgiving conditions of interstellar travel. They must endure extreme acceleration, the initial, powerful shove that propels them towards incredible speeds. They must survive the unimaginable cold vacuum of deep space, where temperatures plummet to near absolute zero. And, crucially, they must be robust enough to endure potential collisions with microscopic space dust, particles that, at such phenomenal speeds, could become devastating projectiles. With all these quiet, immense challenges in mind, perhaps the project would more aptly, though gently, be named Project Breakthrough Longshot. The path to the stars, it seems, is paved not just with dreams, but with an unwavering commitment to overcoming seemingly impossible obstacles. But if the long, patient history of space exploration has taught us anything, it is a profound and beautiful truth. It is that missions, often confronted with cruel hardship, immense technological barriers, and seemingly slim odds of success, can, against all expectations, emerge as triumphant milestones of humanity. Think of the Apollo missions, the Hubble Space Telescope, or those very Voyager probes we just spoke of, each a testament to our collective will to explore, to understand, and to reach for the impossible. Proxima Centauri, our closest stellar neighbor, with all its mysteries and all its challenges, might just be the next such profound entry for the history books. A quiet, humble red dwarf holding the key to humanity's first tentative steps into the vast silent ocean of interstellar space. And as we ponder this magnificent possibility, we can only hope, with a gentle sense of longing, that we are around to witness its grand, quiet unveiling. The future, it seems, is a story that unfolds with both profound slowness and breathtaking speed, always holding new wonders for those who dare to look and to dream. As telescopes like the magnificent James Webb Space Telescope gently unfurl their golden mirrors and look out across the swirling, starlit expanse of our very own Milky Way galaxy, you might have heard a growing, quiet buzz, a gentle hum of excitement and wonder, perhaps around the newly discovered exoplanets that are being unveiled with increasing frequency. It wasn't so long ago, really, a mere whisper in the grand timeline of human discovery. Only in 1992 did we find the very first planet outside our solar system. Think of that, how recent it was, how profound that initial glimpse beyond our immediate cosmic neighborhood. But since that momentous discovery, since that quiet first step, the pace has accelerated with astonishing grace. Over 5,500 exoplanets have now been officially confirmed, each a tiny, distant world added to our cosmic map. And these worlds are not scattered thinly across the entire galaxy. They are clustered within the relatively small area of space, only a few thousand light years across, that we presently reside in. Imagine the sheer scale of our galaxy for a moment. The Milky Way itself is roughly 100,000 light years in diameter, a vast, swirling disk of stars, gas, and dust. And yet, our confirmed exoplanets, these thousands of new worlds, are mostly confined to just a tiny localized pocket of that immense expanse. This humble beginning, this small sample, offers us a truly tantalizing promise. It whispers of billions to trillions more undiscovered worlds stretching across the rest of our galaxy, waiting patiently to be revealed. The thought itself is breathtaking. Isn't it a silent, awe-inspiring testament to the boundless abundance of the universe. It suggests that, on average, every single star you gaze upon in the night sky, every distant flicker of light, likely has at least one planet, and perhaps even several, nestled in its gravitational embrace. The universe, it seems, is teeming with worlds, far beyond our wildest imaginings just a few decades ago. With all of these exoplanets out there, patiently waiting to be found, it is only natural that our thoughts, our deepest human curiosities, would gently turn towards concepts like Goldilocks zones and planet habitability. After all, we humans, in our inherent drive to explore and expand, have always had our eyes on a grander prize colonizing the stars, finding a new home amongst the distant suns, and the idea of an Earth 2.0, a perfect cosmic twin, surely waits for us out there, a beacon of hope in the vast cosmic ocean. Mathematically speaking, and in the quiet logic of probability, such a world seems almost inevitable. In fact, you might have already heard that very phrase, Earth 2.0, being delivered with a certain flourish in the headlines of articles or in the captivating narratives of videos. These often claim that a planet has been discovered, a distant orb, that would be an ideal candidate for human life, and, ultimately, for colonization. The whispers of a new home, a grand escape, can be powerfully alluring, can't they? However, dear listener, let us pause for a moment and with a gentle, discerning mind, offer a quiet word of caution. Do not believe the hype. For all the planets we have found so far, despite the tantalizing whispers, have, to put it scientifically, yet gently, sucked. And once you hear what I am about to share with you, once we peel back the layers of romanticized notions, you will likely agree that moving to any of them would be the very last thing any sane person would want to do. The universe, it seems, is not always as accommodating as our deepest dreams might wish. I am Alex Mounsey, and you are watching Astrom. Join with me today as I give you a grand real estate tour of the potential Earth 2.0s we've discovered so far. We will explore why, right now, with our current understanding and technological limitations, it is precisely the wrong time to get onto the planetary property ladder. Our journey will not be about dashing hopes, but about grounding our profound curiosity in the quiet realities of cosmic existence, understanding the subtle, yet formidable challenges that lie between us and a truly habitable second home. When embarking on the grand cosmic endeavor of choosing an Earth 2.0, much like the more earthly task of building a house, it is always a wise and gentle idea to begin by establishing your non-negotiables. These are the fundamental conditions, the quiet must-haves, that simply cannot be compromised if we are to find a new home in the vastness of space. Some of these considerations are fairly simple, almost intuitive to contemplate, aren't they? They speak to our most basic, primal needs for comfort and survival. For instance, let us consider temperature. When we dream of a new home, we envision a nice, temperate climate, a place where it's not too warm, gently scorching, and certainly not too cold, bitterly freezing. We seek that delicate balance, that perfect equilibrium that allows life to flourish. Given that temperature naturally drops the further you venture from a star, every planetary system, in its own unique configuration, possesses a sweet spot. This is the orbital range where a planet's temperature is likely to be just right, not too hot and not too cold, much like the beloved tale of Goldilocks and her bowls of stolen porridge, finding that perfect, comfortable middle ground. As a rough, gentle rule of thumb, if a planet simply resides at the right distance from its star, it may very well have a suitable temperature for us to set up shop, to begin to imagine a new existence. Of course, this comfortable distance is by no means a guarantee of habitability. The universe, in its intricate complexity, rarely offers such straightforward answers. After all, consider our own solar system. Venus, for example, a planet that, in theory, resides within this very Goldilocks zone of our sun, should, in principle, be perfect. It is at a distance where liquid water could potentially exist, yet its thick, choking atmosphere has transformed it into the hottest planet in our solar system, despite its relative distance from the sun compared to fiery Mercury. This stark example gently reminds us that a planet's atmosphere also plays a profoundly crucial part in all of this. Isn't it? It is not enough to simply be in the right place. The very air, the very blanket of gases that envelops a world, holds the key to its potential as a home. Speaking of atmosphere, that, too, is undoubtedly something you'll want to carefully look for on any potential Earth 2.0. Ideally, we dream of a world with something akin to our own life-giving air, an atmosphere rich with oxygen to breathe and water vapor to cycle and nourish, and crucially, without anything that would gently poison us with its unseen touch. But even if such an ideal composition isn't immediately present, we would, at the very least, hope for an atmosphere that could effectively trap heat in, providing a comforting warmth, and, perhaps most importantly, offer some degree of protection from the relentless onslaught of space radiation. Imagine a delicate shield, invisible yet immensely powerful, guarding a world against the harshness of the cosmic environment. However, sometimes a non-negotiable is not just about the inherent qualities of the planet itself, but simply about the neighbors that live close by. The cosmic context, the immediate stellar environment, can play just as profound a role in a world's habitability as its internal conditions. And so, let us gently shift our focus and consider the first major reason why most of the galaxy's exoplanets, despite their tantalizing presence, quietly fall short of our hopes: the nature of their neighboring stars. Our own beloved star, the radiant heart of our solar system, is known as a G-type yellow dwarf. It is a star in the grand cosmic scheme that burns relatively quickly and has a comparatively short lifespan, at least when stacked against some of the other stellar options out there in the vastness. Stars like our Sun tend to gracefully live for about 10 billion years before their cores gently collapse and they undergo a profound transformation, blossoming into a red giant. And, crucially for us, throughout the vast majority of that lifespan, our Sun maintains a remarkable stability. This gentle, unwavering stability has been utterly vital, an indispensable gift for the life that eventually flourished here on Earth, allowing billions of years for evolution to unfold its intricate dance. However, dear listener, when we cast our gaze across the wider canvas of the Milky Way, we quickly learn a fascinating truth. Yellow dwarfs, stars like our Sun, are far from common. They represent only a modest 10% of the total stars in our galaxy. The universe, it seems, has a different favorite. Far more prevalent, far more common in occurrence, are the long-lived red dwarfs, these quiet, enduring embers that make up a staggering 75% of the stars in our galaxy. Imagine the sheer abundance of these tiny, resilient suns and their lifespan. They can live for an astonishing 14 trillion years, a duration that stretches far, far longer than our universe has even existed. This means quite profoundly that we have, quite literally, never seen one die, never witnessed the end of their long, patient burning. And unfortunately, dear listener, for the planets that might happen to orbit these immensely long-lived red dwarfs, their longevity comes with numerous, rather significant drawbacks. These are not the gentle, nurturing homes we might initially imagine. For starters, red dwarfs possess a much closer Goldilocks zone compared to their larger, yellower cousins. This is because they burn far less brightly, their luminosities ranging from a mere 10% down to an astonishingly faint 0.0125% of our sun's output. Imagine a light bulb that is barely glowing compared to a powerful floodlight. So, unless you desire to live on a world perpetually shrouded in a twilight gloom, a place that sounds cold and, frankly, a little depressing to our sun-loving sensibilities, and which would certainly make growing plants a bit of a challenge, you would want any potential Earth 2.0 orbiting a red dwarf to be a lot nearer to its star to compensate for its dimness. This proximity, in and of itself, wouldn't necessarily be a problem, a deal breaker, if it weren't for the second, and arguably more challenging characteristic of red dwarfs that makes them very unpleasant neighbors, their instability. Our own sun, our familiar star, is the primary source of our space weather. Of course, it gently shoots out a frequent stream of solar winds, the occasional flare, and the grand, majestic coronal mass ejections. These are powerful phenomena, but they are generally manageable, held in check by our planet's protective magnetic field. However, this gentle activity simply does not compare, not even remotely, to the sheer volume and intensity of space weather created by red dwarfs. Flares from red dwarfs, these sudden violent outbursts of energy, can be a staggering 100 to 1,000 times more powerful than those emitted by our sun. Imagine a cosmic storm on an unimaginable scale, a relentless barrage of raw, untamed energy. These frequent, ferocious bursts of plasma and radiation emanating from red dwarfs are powerful and dangerous enough to utterly strip away the atmosphere of any planets orbiting nearby, and, in a terrifying possibility, even boil away any liquid water on planets unfortunate enough to reside within their habitable zone. Think of the delicate balance of life, suddenly obliterated by a cosmic tempest. And given how much closer planets are forced to orbit their star in a red dwarf system to stay warm, the odds of life getting enough time to arise and evolve, to unfold its intricate dance before being hit with a devastating life-sanitizing dose of X-rays is pretty slim indeed. If you were to consider living on a planet around a red dwarf, you would likely need some very serious cosmic-grade sun cream, and perhaps a very, very deep underground bunker, just to survive the relentless onslaught. The experience, even if survivable, would hardly be pleasant, would it? But even during the quiet, fleeting periods between these harsh, violent solar weather events, there's another profound problem that plagues planets orbiting around red dwarfs: their inherent tendency to be tidally locked. We've touched upon this concept before, haven't we? Imagine a gentle, invisible hand, a powerful gravitational tug, holding a planet in an unyielding embrace, preventing it from rotating on its axis. Being tidally locked means that the same side of the planet always faces the star as it orbits. There is no soothing rotation between day and night, no rhythmic progression of light and shadow. Instead, one side of the planet is forever bathed in perpetual heat, a scorching, sun-baked landscape, while the other side is eternally plunged into permanent shadow, a freezing dark expanse. Consider our own solar system. Even here, the subtle influence of gravity can be observed. Look at Mercury, for instance, our innermost planet, with a day that lasts an astonishing 176 Earth days, or 2 Mercurian years. This is a subtle hint of the tidal locking phenomenon. Planets that orbit incredibly close to their suns, due to the powerful gravitational constraints, naturally tend towards being tidally locked. This lack of rotation, this unwavering orientation, would render most of the planet utterly uninhabitable for life as we know it. You would either face scorching, desert-creating heat on the dayside, where any water would quickly boil away into the vastness of space, or you would endure freezing ice on the night side, a desolate, dark realm where liquid water would instantly solidify. Even if humans tried to eke out an existence in the narrow twilight band, the delicate strip between perpetual day and eternal night, that would ring a tidally locked planet, liquid water might prove incredibly difficult to find. Any moisture in the air, any gentle mist that found its way to the perpetually cold night side of the planet would immediately get locked there, solidified as immovable ice. Overall, the entire planet would be profoundly dry, a parched, desolate landscape. And even in that twilight zone, that fragile strip of potential, there would be no rain, no gentle cleansing showers to nourish the land. The very hydrological cycle, so vital for life on Earth, would be fundamentally broken. And that's not to mention another critical consequence of tidal locking, the likely low power of a magnetic field. On Earth, the powerful dynamo effect that generates our protective magnetic field is thought to be profoundly influenced by the Coriolis effect, the subtle swirling force created by our planet's rotation. This rotation imparts momentum to the rising and falling liquid metal in our core, churning it into a giant, self-sustaining electromagnet. Without this fundamental rotation, without this ceaseless churn, such a magnetic field would be inevitably weaker, perhaps even non-existent. And without a robust magnetic field, a planet is utterly vulnerable to the constant, deadly bombardment of space radiation, making any form of surface life incredibly tenuous, if not impossible. So, dear listener, with a gentle sigh of regret, I'm sorry to say that this fundamental characteristic effectively rules out many of our most tantalizing exoplanet candidates, such as Proxima Centauri b, our closest exoplanet. While its proximity makes it one of the easiest planets to get to for us, situated only 4.2 light-years away, and while it is thought to be a rocky, Earth-like planet, a convenient factor, as living on a gas giant would undoubtedly be challenging for anyone with a fondness for solid floors beneath their feet. And most compellingly, its mass and radius are very similar to Earth's, meaning it has a similar gravity. All these factors initially seem so promising, don't they? But the reality of tidal locking and the harsh consequences it brings cast a long, cold shadow over its habitability. Why is similar gravity so important? You might ask. Let's gently compare it with another once promising candidate, a planet that, for a brief, hopeful period, was heralded as the epitome of an Earth 2.0, Kepler 452b. This was the very first planet to ever be referred to by that grand title. The planet described by a NASA scientist with quiet awe as the closest twin to Earth. Kepler 452b certainly had much to recommend it. It is orbiting around a yellow dwarf star, much like our own sun, and at a similar distance. This places it squarely in the Goldilocks zone, making liquid water on its surface a theoretical possibility. However, Kepler 452b is a super-Earth. This classification, while intriguing, means it has a mass and radius combination that makes its gravity about twice that of Earth. Now, how much gravity is too much? Some scientists, delving into this profound question, estimate the figure at about 4 times Earth's gravity as being the approximate limit of what a human could physically survive. But even living in just twice Earth's gravity could become rather uncomfortable. A constant, subtle burden that would shape every aspect of existence. To properly visualize this, or at least get a rough, empathetic approximation of it, try to imagine yourself lying down. Now, gently imagine a second person lying directly on top of you, putting all their weight onto your body. This, dear listener, is what your night would feel like. Every night, on a planet with double gravity. Every breath would be a struggle, fought for against an unseen, crushing weight. And then, come daybreak, you must lift that extra person up, haul them gently onto your back, and then carry them with you everywhere you go. Everywhere. every step, every movement, a monumental effort. And be careful not to fall, for suddenly, breaking a bone would be much easier. Falling downstairs would no longer be merely painful, it would likely be lethal. And this profound burden would apply to everyone: the elderly, the infirm, even small infants trying to take their first wobbling, gravity-defying step. Keeping this vivid image in mind, it becomes easy to grasp just how utterly exhausting, how relentlessly challenging life in double gravity might end up being. For a bodybuilder or an athlete, perhaps it might be manageable, a constant, grueling workout. But for most people on Earth, it would be a slow, relentless torture. Your heart would furiously beat, ceaselessly pumping blood around your body, making it feel like you're constantly running, even when you're simply standing still. And if you were to imagine tripling the gravity, add an additional person on top of that, and things certainly don't get much better, do they? Conversely, what about reduced gravity? If the weight is lifted, everything feels much easier, much lighter. A joyous sense of freedom. However, living under reduced gravity comes with a host of significant health risks, challenges that we have already begun to observe from astronauts who have spent just a few months gently floating on the International Space Station. Over time, the very calcium begins to bleed out of their bones, causing them to become brittle, fragile. Their muscles atrophy, becoming weak and diminished. Their hearts develop issues, adapting poorly to the lack of gravitational pull. Their immune systems suffer, becoming less robust, more vulnerable. All told, even with rigorous daily exercise, their long-term prospects in a low-gravity environment are not looking good. This is a profound fact that profoundly challenges NASA scientists as they try to figure out how to set up human outposts on places like the Moon or Mars, where astronauts might go to live for just a few years. Humans have spent millions of years, vast stretches of evolutionary time, adapting to life on our very specific planet. We are profoundly used to how things are here, to the precise interplay of gravity, atmosphere, and sunlight. We are, quite simply, not suited to anywhere else. We have not evolved to face such extreme conditions, to endure such profound differences. In some respects, it is a testament to how beautifully, how intricately we have acclimatized to the unique environment we were born into, but it is also a very significant, perhaps even insurmountable obstacle if we ever truly wish to live anywhere else. The universe, it seems, has shaped us to be perfectly at home here, making it challenging, if not impossible, to simply pick up and move to a vastly different cosmic address. So, with the gentle yet firm reality that most of the planets we have discovered so far are simply not suitable for human life, either too close to a volatile star, too far from a dim one, or burdened by crushing gravity. Where does that leave our grand, quiet dream of finding an Earth 2.0? It leaves us, dear listener, with a profound, yet perhaps humbling truth. We still have a very, very long way to go. The universe, in its intricate design, does not readily offer up perfect copies of our home. But let us not despair, for the journey of discovery is often as rich and rewarding as the destination itself. And as we continue our gentle exploration, let us turn our thoughts to another crucial aspect of planetary habitability, one that is often overlooked in the initial excitement of discovery, the age of the star and, by extension, the age of the planetary system itself. Our own sun, as we gently discussed, is a G-type yellow dwarf, and it has been burning steadily for approximately 4.5 billion years. This immense span of time has been utterly vital for the intricate dance of life on Earth. It has provided the necessary stability, the consistent flow of energy for simple, single-celled organisms to emerge, to slowly evolve, to diversify, and eventually to give rise to the complex, multicellular life forms that populate our planet today. Imagine the patient unfolding of billions of years, the countless subtle changes, the quiet adaptations, all made possible by the unwavering constancy of our sun. Now, consider a star that is significantly younger than our sun. A star, perhaps, that has only just begun its long, luminous journey. Such a star, and any planets orbiting it, would likely be in a much more turbulent and unstable phase of their existence. Think of a young child, full of boundless energy, prone to sudden bursts of activity and unpredictable shifts in mood. A young star, similarly, is often more prone to violent flares, more powerful stellar winds, and a generally more chaotic environment. For any nascent life trying to take root on a planet orbiting such a star, the conditions would be incredibly challenging. A constant struggle against cosmic volatility. The delicate processes of evolution simply would not have had enough time to unfold, to build the intricate biological machinery necessary for complex life. Conversely, what about a star that is significantly older than our sun? A star that has burned for far longer, perhaps nearing the end of its main sequence lifetime. While such a star might offer a long, stable period for life to emerge, it also presents its own unique set of challenges. As stars age, they gradually begin to swell, to change their luminosity, and to eventually transform into red giants. This expansion would engulf any inner planets, effectively sterilizing them, boiling away any oceans and rendering them utterly uninhabitable. So, there is a delicate window, a sweet spot in a star's lifespan, where it is old enough to have provided sufficient time for life to evolve, yet young enough to not have begun its destructive, final evolutionary phases. This brings us to a profound, yet often overlooked aspect of the universe, the metallicity of a star. Now, when astronomers speak of metals, they are using a very specific, almost poetic definition. In the cosmic lexicon, anything heavier than hydrogen and helium is considered a metal. This includes elements like carbon, oxygen, nitrogen, and iron, the very building blocks of planets, and indeed, of life itself. The metallicity of a star is essentially a measure of how much of these heavier elements it contains. Why is this important? Because stars with higher metallicity are more likely to have rocky planets orbiting them. Think of it like this: when a star forms from a vast cloud of gas and dust, the heavier elements, the metals, tend to clump together, forming the raw material for planets. A star born from a cloud, rich in these heavier elements, will have a more substantial planetary nursery around it, increasing the likelihood of rocky worlds forming. Conversely, a star with very low metallicity, predominantly made of hydrogen and helium, is more likely to be surrounded by gas giants, or perhaps no planets at all. And while gas giants are fascinating in their own right, they are, as we gently noted earlier, not ideal candidates for human colonization. We prefer solid ground beneath our feet, don't we? So, when we consider the grand cosmic timeline and the evolution of the universe itself, we find a fascinating pattern. The very first stars to form after the Big Bang, the universe's initial fiery breath, were almost entirely composed of hydrogen and helium. These were the population 3 stars, massive, short-lived, and utterly devoid of the heavier elements necessary for rocky planet formation. As these first stars lived and died, exploding in magnificent supernova, they forged and scattered the heavier elements into the interstellar medium, enriching the cosmic soup for subsequent generations of stars. This means that stars that formed later in the universe's history, stars like our Sun, which are population 1 stars, are richer in metals. They are the offspring of earlier stellar generations, inheriting the cosmic legacy of heavier elements. This implies that the earlier in the universe's history you look, the less likely you are to find stars with high metallicity, and therefore the less likely you are to find rocky planets. This is a subtle, yet profound filter on our search for Earth 2.0. It suggests that the sweet spot for finding truly habitable worlds might be in a particular cosmic epoch, a time when stars were rich enough in the building blocks of planets, yet still young enough to offer billions of years of stable evolution. And this brings us to another subtle yet significant challenge in our quest for an Earth 2.0, the orbital eccentricity of a planet. Imagine a planet's path around its star not as a perfect, gentle circle, but as an elongated, slightly squashed ellipse. This is what we call an eccentric orbit. Our own Earth, for example, has a very low orbital eccentricity, meaning its path around the Sun is almost perfectly circular. This ensures a relatively consistent distance from the Sun throughout the year, leading to stable, predictable seasons and a relatively consistent temperature. However, many of the exoplanets we have discovered so far exhibit highly eccentric orbits. This means that at certain points in their year, they swing incredibly close to their star, experiencing scorching, intense heat, and then, at other points, they drift far away, plunging into bitter, freezing cold. Imagine a world experiencing extreme, rapid temperature swings, oscillating between a fiery inferno and a frozen wasteland within a single orbital period. Such dramatic fluctuations would make it incredibly challenging for liquid water to persist on the surface, and even more so for life to adapt and thrive. The constant, violent shifts would be a relentless assault on any delicate biological systems. The universe, it seems, has a myriad of ways to make a world inhospitable, even if it appears to be in the right Goldilocks zone on average. So, when we combine all these factors, the type of star, its age, its metallicity, and the orbital eccentricity of its planets, the picture of finding a truly habitable Earth 2.0 becomes far more nuanced, far more challenging than the initial headlines might suggest. The universe, in its vastness, is not simply waiting to hand us a ready-made second home. It demands patience, precision, and a deep understanding of its intricate, often unforgiving laws. Let us now gently turn our attention to one of the most remarkable and perhaps most humbling aspects of our cosmic existence, the rare Earth hypothesis. This hypothesis, a quiet whisper in the scientific community, suggests that the emergence of complex, intelligent life, like that found on Earth, may be an exceptionally rare event in the universe. It proposes that a unique combination of astrophysical and geological events, a delicate interplay of cosmic coincidences, was necessary for our planet to become the vibrant, living world it is today. Think of it as a cosmic lottery, where the odds of winning are astronomically low. The rare Earth hypothesis posits that not only do you need a planet in the right Goldilocks zone, orbiting the right type of star, at the right age, with the right metallicity, and a near-circular orbit, but you also need a whole host of other, more subtle, yet equally crucial, factors. For instance, consider the presence of a large moon. Our own moon, a silent, majestic companion, plays a vital role in stabilizing Earth's axial tilt, preventing dramatic, chaotic wobbles that would lead to extreme climate fluctuations. Without our moon, Earth's climate would be far more unstable, making the long-term evolution of complex life much more challenging. The moon also creates the tides, which some theories suggest played a role in the very emergence of life from the primordial oceans. Then there's the presence of gas giants in the outer solar system. Jupiter, our massive, protective guardian, acts like a cosmic vacuum cleaner, gravitationally sweeping up dangerous asteroids and comets that might otherwise impact Earth. Without Jupiter's benevolent presence, Earth would likely experience far more frequent and devastating impacts, making the sustained evolution of complex life much more difficult. Furthermore, the rare Earth hypothesis emphasizes the importance of plate tectonics. This geological process, the slow, majestic movement of Earth's crustal plates, plays a crucial role in regulating our planet's climate through the carbon cycle, recycling essential nutrients, and creating the diverse geological features that contribute to biodiversity. Without plate tectonics, Earth might have become a barren, lifeless world, much like Venus or Mars. And let us not forget the right kind of galaxy. Our Milky Way, a spiral galaxy, is considered a relatively safe place for life. In the galactic center, where stars are densely packed and supermassive black holes lurk, the environment is far too harsh, too filled with intense radiation and frequent stellar encounters for life to thrive. Similarly, in the galactic outskirts, the metallicity of stars tends to be lower, making rocky planet formation less likely. Our solar system, nestled in the galactic habitable zone, a gentle sweet spot between the chaotic center and the barren periphery, offers a relatively stable and metal-rich environment. The rare Earth hypothesis, therefore, paints a picture of our planet as a truly unique cosmic gem, a rare confluence of fortunate circumstances. It suggests that while simple microbial life might be common throughout the universe, complex, intelligent life, capable of building civilizations and pondering its place in the cosmos, might be exceedingly rare. This perspective, while perhaps a little melancholic to our grandest dreams of interstellar colonization, also fills us with a profound sense of awe and gratitude for the precious, delicate miracle that is life on Earth. It reminds us to cherish and protect this singular home, for its like may not be easily found elsewhere in the vast, silent expanse. So, with all these complex factors in mind, it becomes clear that the search for an Earth 2.0 is not merely about finding a planet of similar size and temperature. It is about finding a world that meets a highly specific and often subtle set of criteria, a cosmic needle in a truly immense haystack. And this leads us to the profound, yet often unasked, question, why are we so desperate to find an Earth 2.0 in the first place? Why this relentless, almost primal, drive to find a new home amongst the stars? Perhaps it stems from a deep-seated human desire for expansion and exploration. We are, by our very nature, explorers, driven to push the boundaries of our knowledge and our physical reach. The vastness of space beckons, and the idea of new frontiers, new worlds to discover, and perhaps even inhabit, is powerfully alluring. It speaks to the adventurous spirit within us, the quiet yearning for the unknown. Or perhaps it is born from a more pragmatic, yet equally profound, concern, the long-term survival of humanity. We are increasingly aware of the fragility of our own planet, the delicate balance of its ecosystems, and the potential threats that loom, both natural and self-inflicted. The idea of having a backup plan, a second home amongst the stars, offers a sense of security, a safeguard against the potential demise of our civilization on Earth. It is a quiet acknowledgement of our own vulnerability and a testament to our inherent drive for self-preservation. And then there is the profound, almost spiritual dimension. The search for other habitable worlds is, in essence, a search for meaning and connection in the vast, silent cosmos. Are we alone? Are there others out there, pondering the same grand questions, gazing at the same distant stars? The discovery of another living world, another Earth 2.0, would not only be a scientific triumph, but a philosophical revelation, profoundly altering our understanding of our place in the universe. It would be a testament to the abundance of life, a quiet reassurance that we are not singular, not isolated, but part of a grand cosmic tapestry of existence. However, Dear listener, let us gently remind ourselves of a crucial truth. We are not going to colonize other planets anytime soon. The technological hurdles, the sheer scale of the distances, and the unforgiving nature of even the most habitable exoplanets make such a prospect a distant dream, perhaps many centuries, or even millennia, away. The romanticized notions of interstellar travel and planetary colonization, so prevalent in our science fiction, often gloss over the immense, almost insurmountable, challenges that lie between us and such a future. The truth is, even if we were to find a perfect Earth 2.0 tomorrow, a world that miraculously met all our criteria for habitability, the journey there would still be an undertaking of unimaginable scale. As we discussed with Project Breakthrough Starshot, even reaching our closest stellar neighbor, Proxima Centauri, is a monumental challenge, requiring revolutionary technologies that are still very much in their infancy. And Proxima Centauri is just over 4 light-years away. The vast majority of the exoplanets we have discovered are hundreds, even thousands, of light-years distant. The sheer energy required to propel a spacecraft, let alone a human crew, across such immense distances, at speeds that would make the journey feasible within a human lifetime, is currently beyond our wildest capabilities. Furthermore, even if we could reach such a world, the challenges of terraforming it, transforming an alien environment to make it truly hospitable for human life, are equally daunting. Imagine altering an entire planet's atmosphere, its temperature, its hydrological cycle, its very geology, to suit our needs. It is a task that borders on the godlike, requiring resources and technologies that are currently far beyond our grasp. The idea of simply stepping off a spaceship onto a new planet and immediately beginning to build a new civilization is, for now, a beautiful, yet ultimately unrealistic fantasy. So, what does this mean for our quiet dream of an Earth 2.0? It means that for the foreseeable future, Earth is our only home. This beautiful, vibrant, fragile planet, with its delicate balance of life, its nurturing atmosphere, and its perfect distance from our benevolent sun, is the only place in the vast, silent cosmos where we can truly thrive. It is a unique and precious gift, one that we must cherish, protect, and nurture with all our collective wisdom and effort. Instead of pouring vast resources into the distant, uncertain dream of finding and colonizing another planet, perhaps our efforts would be better spent, more gently and effectively, on preserving and restoring the planet we already have. Imagine if the same ingenuity, the same dedication, the same immense resources that we contemplate for interstellar travel were directed towards solving the pressing environmental challenges facing Earth climate change, biodiversity loss, resource depletion. What a profound transformation we could achieve right here, right now, on our one and only home. The search for exoplanets, the quiet unveiling of distant worlds, is undoubtedly a magnificent scientific endeavor, one that expands our understanding of the universe and our place within it. It fuels our curiosity, inspires our imagination, and reminds us of the boundless wonders that lie beyond our immediate grasp. But let us not allow this grand cosmic quest to overshadow the profound, immediate responsibility we have to our own planet, for now, and for the foreseeable future. Earth is our Earth 1.0, and it is the most precious, most truly habitable world we will ever know. Let us treat it with the reverence and care it deserves, for it is the cradle of our existence, the silent witness to our history, and the only true home we have in this vast, wondrous, and often unforgiving universe. The stars will always be there, beckoning us with their distant light, but our most immediate and profound journey, the one that truly matters for our survival and well-being, is the journey inward, towards a deeper understanding and appreciation of the miraculous world beneath our feet. As we gently drift through the vast, silent ocean of cosmic thought, having pondered the immense challenges of finding a truly habitable Earth 2.0, our minds might naturally turn inwards towards the very fabric of our own existence. And in that quiet contemplation, one concept stands out, both profoundly simple and endlessly complex: time. What is time? Really, is it a relentless river, always flowing forward, carrying us irrevocably from past to future? Or is it something more elusive? A dimension we navigate, a construct of our perception. The questions whisper to us, don't they, as we lie here, suspended in this moment of tranquil reflection. You have surely felt its relentless march, haven't you? The quiet tick-tock of a clock, the subtle shift from day to night, the steady progression of seasons. We experience time as a linear progression, a continuous stream from a definite past through an ever-fleeting present into an uncertain future. This intuitive understanding, this deeply ingrained perception, shapes our entire reality. We plan for tomorrow, we remember yesterday, and we live moment by moment in the now. But is this how the universe truly experiences time? Or is our human perception merely a limited window into a far grander, more mysterious reality? For centuries, millennia even, philosophers and scientists have grappled with this very question. Ancient civilizations observed the predictable cycles of the sun and moon, the rhythmic dance of the stars, and built their lives around these celestial clocks. They understood time as a series of recurring events, a cyclical pattern of birth, growth, decay, and renewal. Yet, even then, the underlying nature of time, its fundamental essence, remained a profound enigma. Is it an independent entity, a fundamental dimension of the universe, existing regardless of anything within it? Or is it merely a measure of change, a way for us to quantify the unfolding of events? It was Isaac Newton, in his grand mechanistic view of the universe, who famously proposed the idea of absolute time. For Newton, time was like an invisible, unchanging river, flowing uniformly and independently of everything else. It was a universal clock, ticking away at the same rate for everyone, everywhere, regardless of their motion or location. Imagine a cosmic metronome beating out a steady, unwavering rhythm for the entire universe. This concept, so intuitively appealing, dominated scientific thought for centuries. It provided a stable framework for understanding the movements of planets, the trajectories of projectiles, and the predictable unfolding of physical laws. In this Newtonian universe, time was a backdrop, a stage upon which the drama of existence unfolded, but not an active participant in the play itself. It was simply there, an unyielding, immutable constant. However, as the gentle whispers of scientific inquiry grew louder, and as our understanding of the universe deepened, the Newtonian view of absolute time began to show subtle cracks. The first faint tremors came with the study of light and the perplexing constancy of its speed. No matter how fast you moved, no matter how fast the source of light moved, the speed of light in a vacuum always seemed to be the same. This was a profound puzzle, one that defied the intuitive logic of Newtonian physics. If time was truly absolute, and light was a wave, then its speed should surely change depending on the observer's motion, just as the speed of a sound wave changes if you are moving towards or away from its source. But light, it seemed, was different. It held its speed with an unwavering, almost defiant constancy. And then, into this quiet scientific conundrum, stepped a young, audacious mind, Albert Einstein. His theories of special relativity in 1905 and later General relativity in 1915 profoundly reshaped our understanding of time, transforming it from a mere backdrop into an active, dynamic participant in the cosmic drama. Einstein's genius lay in his willingness to challenge deeply held assumptions, to follow the quiet logic of the universe wherever it led, even if it defied our everyday intuition. In special relativity, Einstein revealed a breathtaking truth: time is not absolute. Instead, it is relative to the observer's motion. Imagine two people, one standing still and another traveling at an incredibly high speed. For the person moving at high speed, time would actually slow down relative to the person standing still. It's a phenomenon known as time dilation. The faster you move, the slower time passes for you. This is not a trick of perception. It is a fundamental property of the universe. Think of it like this: if you were to travel near the speed of light, you could journey across vast cosmic distances in what would feel like mere moments to you. While centuries might pass back on Earth, your clock would tick slower, your aging process would slow, all relative to someone who remained stationary. It's a concept that sounds like science fiction, yet it has been repeatedly confirmed by countless experiments, from atomic clocks on airplanes to the behavior of subatomic particles in accelerators. And then, with general relativity, Einstein took this revolutionary idea even further. He showed that time is not only relative to motion, but also to gravity. Imagine a massive object like a star or a planet. Its immense gravitational pull actually warps the fabric of space-time around it, creating a kind of dent in the cosmic tapestry. And within this warped space-time, time itself slows down. The stronger the gravitational field, the slower time passes. This is known as gravitational time dilation. If you were to stand on the surface of a neutron star, an incredibly dense remnant of a collapsed star, time would pass significantly slower for you than for someone far away in interstellar space. Even here on Earth, time passes ever so slightly slower at sea level than it does on top of a mountain, due to the subtle difference in gravitational pull. These effects are minuscule in our everyday lives, but they are real, and they are profoundly important for technologies like GPS, which rely on incredibly precise timing. So, for Einstein, time was not a separate, independent entity, but rather inextricably woven into the very fabric of the universe, part of a unified whole called space-time. Imagine a vast, flexible sheet, a cosmic trampoline, where space and time are two sides of the same coin. Massive objects create curves and ripples in this sheet, and these curves dictate how objects move and how time itself flows. This revolutionary concept transformed our understanding of reality, revealing a universe far more dynamic and interconnected than Newton could have ever imagined. But even with Einstein's profound insights, the mystery of time lingers. Why does time seem to flow only in one direction, from past to future? Why do we never experience time running backward? This is the perplexing concept of the arrow of time. The laws of physics, at their most fundamental level, are largely time-symmetric. They work just as well if time runs forward or backward. Yet, in our everyday experience, time is undeniably unidirectional. A dropped glass shatters. It never spontaneously reassembles. An egg scrambles. It never unscrambles. We remember the past, but we cannot remember the future. One of the most compelling explanations for the arrow of time lies in the concept of entropy, a fundamental principle of thermodynamics. Entropy is, in essence, a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time, or remain constant. It can never decrease. In simpler terms, The universe, left to its own devices, tends towards greater disorder. Imagine a perfectly organized room. Over time, without any effort, it naturally becomes messy. You never see a messy room spontaneously organize itself. This relentless march towards greater disorder, this cosmic tendency towards increasing entropy, is what gives time its direction. The past is a state of lower entropy, and the future is a state of higher entropy. We remember the past because it is a more ordered state, and we move towards the future because that is the direction of increasing disorder. This concept has profound implications for the universe as a whole. From the initial, highly ordered state of the Big Bang, the universe has been steadily expanding and becoming more disordered, its entropy constantly increasing. This cosmic expansion, this relentless drive towards greater randomness, is what gives the universe its own grand arrow of time, and it suggests that time, as we experience it, is not merely a human construct, but a fundamental property of the universe's evolution, driven by the inexorable march of entropy. However, the nature of time becomes even more perplexing when we delve into the realm of quantum mechanics, the physics of the very small. At the quantum level, the neat, predictable flow of time seems to break down. Particles can exist in multiple states simultaneously, and events can appear to happen without a clear cause and effect relationship. Some interpretations of quantum mechanics even suggest that time might not be a fundamental property at all, but rather an emergent phenomenon, something that arises from the interactions of particles at a deeper level. Imagine time as a symphony, where the individual notes quantum events don't necessarily have a clear temporal order, but when played together, they create the illusion of a flowing melody. This leads to some truly mind-bending ideas, such as the concept of a timeless universe. Some physicists propose that at the most fundamental level, there is no such thing as time. Instead, the universe exists as a vast, interconnected network of events, a block universe where past, present, and future all exist simultaneously. Our perception of time's flow, they suggest, is merely a consequence of our consciousness, our unique way of navigating this timeless reality. Imagine a book, where all the pages exist at once, but we can only read them one after another, creating the illusion of a story unfolding in time. And what about the very beginning of time? Did time have a beginning, or has it always existed? The Big Bang Theory, our current best model for the origin of the universe, suggests that time itself began with the Big Bang, approximately 13.8 billion years ago. Before that moment, according to this theory, time, space, and matter as we know them simply did not exist. It's a concept that challenges our intuition, our deeply ingrained notion that there must always be a before. But if time itself began with the Big Bang, then asking what happened before the Big Bang is like asking what is north of the North Pole. The question itself loses its meaning. However, some alternative theories, such as cyclic universe models, propose that the universe undergoes an endless series of Big Bangs and Big Crunches, constantly expanding and contracting in an eternal cycle. In these models, time might not have a beginning or an end, but rather an infinite, recurring loop. Imagine a cosmic pendulum swinging back and forth through eternity, each swing representing a new universe. Even more intriguing are theories that suggest time might be an illusion. Some physicists, grappling with the incompatibility between general relativity, which describes gravity and space-time on large scales, and quantum mechanics, which describes the universe on very small scales, propose that time might not be a fundamental reality, but rather an emergent property that arises from the interaction of other, more fundamental, timeless entities. It's a concept that challenges our very perception of reality, inviting us to consider that the flow of time, so central to our experience, might be a grand cosmic illusion. So, as we gently ponder these profound questions, we are left with a sense of wonder and perhaps a touch of humility. Time, this seemingly simple concept that governs our every moment, is, in reality, one of the deepest and most perplexing mysteries of the universe. It is relative. It is influenced by gravity. It is linked to entropy. And its very nature might be an illusion. The more we learn about it, the more we realize how much we still don't know. But perhaps, in this quiet contemplation, there is a profound comfort. If time is not a rigid, absolute entity, but something more fluid, more dynamic, then our experience of it, our moments of joy and sorrow, our hopes and dreams, become even more precious. They are not merely fleeting points on an unyielding timeline, but vibrant, unique expressions within the flexible tapestry of space-time. And as we lie here, suspended in this tranquil moment, allowing our minds to wander through the grand concepts of time, we can feel a gentle shift in our own perception. The urgency of the clock, the pressure of deadlines, the weight of past regrets or future anxieties, they begin to recede, don't they? Replaced by a quiet acceptance of the present, a profound appreciation for the unfolding now. Perhaps in this very moment, as you breathe softly and let your thoughts drift, you are experiencing a form of time dilation, a gentle slowing of the cosmic clock, simply by allowing your mind to be still. The external world might continue its relentless pace, but within your own consciousness, time can stretch, expand, and become a space for quiet reflection, a sanctuary from the ceaseless rush. This is not a call to abandon the practicalities of life, or to ignore the responsibilities that time imposes upon us. Rather, it is an invitation to cultivate a deeper relationship with time, to recognize its profound mystery, and to appreciate the preciousness of each passing moment. For in the grand cosmic dance of space-time, every second, every breath, every quiet thought is a unique and irreplaceable event, woven into the eternal fabric of the universe. And as we gently conclude this chapter on the enigmatic nature of time, we can feel its subtle presence all around us, in the quiet rhythm of our breath, in the distant hum of the world, and in the slow, patient unfolding of our own thoughts. It is a mystery that continues to beckon, inviting us to delve deeper, to question further, and to simply marvel at the profound beauty of its existence. The universe, it seems, is a master of paradox, offering us a concept that is both utterly familiar and endlessly alien, a constant reminder of the boundless wonders that lie just beyond the veil of our everyday perception. As we gently drift through the vast, silent ocean of cosmic thought, having pondered the immense challenges of finding a truly habitable Earth 2.0, and having meditated upon the enigmatic nature of time, our minds might naturally turn towards another concept, equally profound and often overlooked: silence. Within the boundless expanse of the universe, silence reigns supreme, a profound, almost absolute silence, stretching across the vast distances between galaxies, between stars, and even in the most tranquil moments of our very own planet. What is this silence? Really, is it merely the absence of sound, a void where vibrations cease, or does it hold a deeper meaning, a presence of its own, a foundational state upon which the universe unfolds in our hurried, noisy daily lives? We often associate silence with emptiness, with barrenness, or sometimes with a touch of loneliness. We instinctively fill silence with music, with chatter, with the constant hum of modern existence. But in the universe, silence is a fundamental condition, an invisible shroud that envelops nearly everything. Imagine, if you will, an astronaut, gently untethered, drifting slowly in the profound blackness of space, far, far away from the familiar clamor of Earth. Here, there is no air to carry sound waves, no medium for vibrations to travel. There is only an absolute quiet, a stillness so profound it can almost feel overwhelming. Even the most powerful supernova explosions, the most violent and cataclysmic events in the cosmos, unfold in utter silence to an observer without specialized equipment. This is the silence of the vacuum, a physical silence, but one that also evokes a deeper, more philosophical stillness, a quiet invitation to contemplate. It is a quiet so deep that your own heartbeat might become the loudest sound, a gentle drumbeat in the profound cosmic hush, reminding you of the fragile living symphony within. This cosmic silence, does it whisper of profound loneliness? For centuries, millennia even, human beings have gazed up at the night sky, their hearts filled with the ancient universal question, are we truly alone in this boundless universe? This question, famously encapsulated in what we call the Fermi paradox, quietly asks if the universe is so vast, so incredibly old, and if there are so many planets seemingly capable of nurturing life, then why have we not yet found any definitive signs of life beyond Earth? Why are there no voices echoing back to us from the distant stars? Why this pervasive, haunting silence? The great silence of the universe, this deep, pervasive quiet, could indeed be a profound answer to this paradox. Perhaps intelligent life truly is exceedingly rare, a precious cosmic anomaly, so fragile and fleeting that it rarely takes root. Or perhaps, once it does, it struggles to endure. Or perhaps the vast echoing silence is because advanced civilizations, once they reach a certain point in their technological prowess, tend to self-destruct before they can develop sufficiently to make contact with us, their own brilliant light extinguished by internal turmoil or technological overreach. Or it might be that we are simply searching in the wrong ways, listening for signals that are not there. Or perhaps we are not yet developed enough to recognize the subtle, sophisticated communications that other, vastly different intelligences might be sending across the cosmic expanse. They may be broadcasting, but we lack the cosmic ears to truly hear. Whatever the reason, this profound silence is a powerful, humbling reminder of our potential isolation within the grand, indifferent expanse of the cosmos. It urges us to cherish the vibrant, noisy, living miracle that is our own planet. But let us consider another perspective, a gentler, more hopeful thought. Silence, after all, is not merely the absence of sound. It is often a fertile ground, a boundless canvas for creation and discovery. In the deep, resonant silence of the universe, scientists have patiently learned to listen for the faint, almost imperceptible echoes of the cosmic microwave background CMB radiation. This ancient whispering hum, a gentle afterglow of the Big Bang, carries within its subtle fluctuations the primordial information about the very dawn of time, the earliest moments of our universe's existence. It is a silent echo that speaks volumes to those who know how to listen. In this profound, quiet, magnificent telescopes like the James Webb Space Telescope have meticulously gathered the faintest light from the most distant galaxies, silently revealing secrets about the very formation and evolution of the universe, painting a breathtaking picture of cosmic history with the oldest photons. Silence, in this sense, is not emptiness. It is a pristine, waiting canvas, a boundless space for us to fill with our questions, with our boundless curiosity, and with our awe-inspiring discoveries. Imagine a skilled composer who does not define a beautiful piece of music merely by the notes played, but by the thoughtful, intentional pauses between them, creating tension, emotion, and profound meaning. The universe, in its grand composition, uses silence to emphasize the moments of existence, the blazing birth of stars, the graceful swirl of galaxies, the quiet, rhythmic orbit of planets. The silence is the space that allows the music of the cosmos to truly resonate, to be truly heard. And within the gentle rhythm of our own lives, silence holds an equally profound and vital role. In a world constantly overflowing with noise, with ceaseless information, with endless distractions, moments of genuine silence become incredibly precious. They are the rare, quiet opportunities where we can truly listen to the inner voice, to delve into deep thought, and to reconnect with our authentic selves. Meditation, contemplation, and those cherished moments of tranquil solitude in nature are all ways in which we instinctively seek out silence, not as an escape from sound, but as a path to finding inner peace, to gaining clarity amidst the chaos, and to simply be present. Silence is also an indispensable, almost invisible component of art and music. A truly great musical piece is not solely defined by the notes themselves, but just as profoundly by the intentional pauses, the silent breaths between them. These silent gaps create rhythm, tension, and emotional depth, allowing the listener's mind to fully engage with the unfolding melody. Similarly, a painting is not merely about its colors and shapes, but also about the negative space, the visual silence that allows our eyes to rest and our minds to contemplate the composition as a whole. A compelling story, too, is not just about the words spoken, but about the unspoken, the quiet gaps, the implied meanings, the spaces left for our own imaginations to fill. Silence, in these artistic realms, is a powerful tool, shaping perception and enhancing understanding. Across diverse cultures and spiritual traditions, silence is often intimately linked with the sacred, with the transcendent, with that which lies beyond our ordinary comprehension. Many religious and spiritual traditions actively encourage silence as a profound pathway to enlightenment, a sacred conduit to connect with the divine, or to experience a deeper reality. In the deep stillness of silence, we might feel more acutely the vastness of the universe, the poignant smallness of our individual selves, and yet, paradoxically, our profound, unwavering connection to something infinitely larger than ourselves. It is in these moments of quiet reverence that the boundary between the inner world and the outer cosmos seems to gently blur, inviting us into a deeper sense of belonging. Yet, we must also acknowledge that silence can, at times, be profoundly unsettling, even frightening. For some, silence is intimately synonymous with loneliness, with isolation, or with a terrifying emptiness in a world where we are constantly surrounded by sound and stimulation, where every moment is often filled with information and entertainment. Silence can feel uncomfortable, even alarming. We might fear the thoughts and emotions that silence can awaken, the quiet truths about ourselves that we often try to keep hidden beneath the relentless din of noise. We may unconsciously use constant sound as a shield, a barrier between us and the unvarnished reflections of our own minds. But if we can gently learn to accept, and indeed, to embrace silence, to invite it into our lives rather than pushing it away, we can begin to discover its immense, transformative power. Silence can reveal itself as a wise teacher, a patient guide, a boundless space for us to grow, to learn, and to truly understand. It can help us to listen more deeply to the subtle whispers of the world, to observe with greater nuance and sensitivity, and to gain a more profound understanding of the universe around us, and, crucially, of our own intricate inner landscape. It is in the quiet moments that clarity often emerges, like a faint light in a misty morning. And in the context of the universe, this grand cosmic silence is a constant, gentle reminder of its immense scale, its boundless mystery, and its ceaseless unfolding. It is an unwavering invitation for us to continue exploring, to continue asking profound questions, and to continue searching for the faint echoes of life and meaning within the vast, echoing expanse of space. The silence, therefore, is not an ending. It is merely the prelude, the opening chord of a cosmic conversation, a quiet beckoning for us to listen more intently to what the universe is patiently trying to whisper to us. Imagine a tranquil moment in the deep of night as you gaze up at the starlit sky. There is no intrusive city noise, no jarring distractions from the hurried pace of daily life. There is only you and the universe, enveloped in a profound, almost tangible silence. In that sacred moment, you can feel the sheer immensity of space, the ancient wisdom of time, and the humbling smallness of your own being. But paradoxically, you can also feel an intimate connection, a profound sense of belonging to something far, far greater than yourself. The silence is not an emptiness. It is a fullness, a gentle embrace. The silence of the universe is not a barren silence. It is a silence pregnant with potential, a silence waiting patiently to be filled by our grand discoveries, by our enduring questions, and by the faint, shimmering echoes of life that may one day answer our call. It is a quiet reminder that even in the most immense reaches of space, even in the most profound moments of stillness, there is always something stirring, a story quietly being told, a mystery patiently waiting to be unveiled. And as we gently conclude this chapter on the profound, enveloping silence, let its quiet essence resonate within your mind. Let it gently remind you of the subtle power of stillness, of the deep beauty found in the absence of noise, and of the profound discoveries that can be made in the most tranquil moments of both life and the vast, whispering universe. Silence is not something to fear. It is something to embrace, something from which to learn, and something to cherish, for it holds secrets that only a quiet mind can discern. Having gently journeyed through the vast, enveloping silence of the cosmos and the intricate dance of time, our thoughts might now softly settle upon another fundamental concept, one that underpins all that we have explored and all that we perceive space itself. What is space? Is it simply the emptiness between things, a passive stage upon which the universe performs its grand drama, or is it something more profound, something active, something that can bend, stretch, and even ripple? The questions whisper to us, don't they, as we lie here, suspended in this moment of tranquil reflection, inviting our minds to wander into its boundless depths. For much of human history, space was largely considered a static, unchanging backdrop. Isaac Newton, whose ideas on absolute time we previously touched upon, also conceived of absolute space. For him, it was like a vast, invisible, unchanging grid, an infinite container that existed independently of anything within it. Whether there were stars, planets, or nothing at all, this absolute space would always be there, rigid and immovable. Imagine a boundless, perfectly uniform canvas, stretched taut and unyielding, waiting for the universe to paint its picture upon it. This Newtonian view, so intuitively appealing, provided a stable framework for understanding how objects moved and interacted within a fixed arena. It was a comforting thought, a solid ground beneath the cosmic dance. However, just as with time, the gentle whispers of scientific inquiry, particularly with the advent of Albert Einstein's theories of relativity, began to subtly reshape our understanding of space. Einstein didn't just revolutionize time, he profoundly transformed our perception of space, weaving it inextricably with time into a unified fabric he called space-time. This was a radical departure from the Newtonian view, moving from a static backdrop to a dynamic, responsive entity. In general relativity, Einstein revealed that space is not merely empty, it is a flexible, deformable entity that can be warped and curved by the presence of mass and energy. Imagine, if you will, a vast, taut rubber sheet. If you place a heavy bowling ball in the center of this sheet, it creates a depression, a gentle curve. Now, if you roll a marble across the sheet, it doesn't move in a straight line. Instead, it follows the curve created by the bowling ball. This, in essence, is how gravity works, according to Einstein. Massive objects, like stars and planets, create dents or curves in the fabric of space-time, and what we perceive as gravity is simply the motion of objects following these curves. This means that space itself is not passive. It is an active participant in the cosmic dance. It dictates how light travels, how planets orbit, and how galaxies are drawn together. The universe is not just in space, it is made of space-time. This revolutionary concept led to profound predictions, such as the bending of light by gravity, which was famously confirmed during a solar eclipse in 1919, solidifying Einstein's vision. Imagine the quiet awe of scientists observing distant starlight curving around our sun, a visible testament to the invisible warping of space itself. But what about the very nature of this fabric? Is it smooth and continuous, like an infinitely stretchable sheet? Or is it, at its very deepest level, composed of discrete, tiny bits, like pixels on a cosmic screen? This is where the profound mystery of quantum gravity gently enters our thoughts, attempting to reconcile Einstein's smooth, continuous space-time with the probabilistic, quantized world of quantum mechanics. At the quantum scale, the universe behaves in ways that defy our everyday intuition. Particles don't have definite positions. They exist as probabilities. Energy comes in discrete packets, or quanta. If space, like everything else, is fundamentally quantized, then it might not be a smooth continuum at all. Instead, it might be made up of incredibly tiny fundamental quanta of space, perhaps like a fine, granular foam. Imagine peeling back the layers of reality, deeper and deeper, until you reach a point where space itself is no longer continuous, but a shimmering, vibrating network of discrete, unimaginably small loops or grains. This is the realm of theories like loop quantum gravity, which proposes that space-time itself is built from these fundamental, quantized loops. It's a breathtaking thought, isn't it? That the very emptiness around us might be woven from discrete, energetic threads, vibrating with the silent hum of the universe's most fundamental structure. This implies that if you were to magnify space to an unimaginable degree, far beyond what any microscope could ever achieve, you would eventually reach a point where the smooth fabric dissolves into a bubbly, frothing quantum foam, a shimmering, uncertain sea of possibility. In this view, space is not a mere stage, but a dynamic, effervescent entity, constantly bubbling and fluctuating at scales far beyond our current grasp. It's a profound shift in perspective, transforming our understanding of emptiness itself. And then there is the question of the universe's expansion. We know, from the gentle whispers carried by the light from distant galaxies, that the universe is not static. It is actively, relentlessly expanding. Imagine a giant balloon, and galaxies are dots painted on its surface. As the balloon inflates, the dots move farther and farther apart, not because they are moving through the surface, but because the surface itself is stretching. Similarly, space itself is expanding, carrying galaxies along with it. This expansion is not just the movement of matter in space, but the expansion of space itself. This expansion, once thought to be slowing down, was discovered in the late 1990s to be accelerating. An astonishing revelation, wasn't it? It suggests that some mysterious, unseen force, which we call dark energy, is gently pushing the fabric of space apart, driving its expansion at an ever-increasing rate. Dark energy, a profound enigma, makes up about 68% of the total energy density of the universe, yet its nature remains one of the deepest mysteries in cosmology. It's like an invisible hand, subtly yet powerfully, guiding the fate of the cosmos, dictating how space itself will unfold into the infinite future. The universe, it seems, is not merely expanding, it is actively, almost eagerly, pushing itself outwards into realms we can barely comprehend. This accelerating expansion has profound implications for our future cosmic view. As space stretches, distant galaxies are being carried away from us at ever-increasing speeds, eventually moving faster than the speed of light relative to us. This means that, in the far distant future, if this acceleration continues, many of the galaxies we can currently observe will eventually drift beyond our cosmic horizon, their light forever unable to reach us. Imagine a future where the night sky, currently teeming with countless brilliant galaxies, becomes a vast, empty expanse, save for our own local group of galaxies. It's a sobering thought, a gentle reminder of the fleeting nature of our cosmic window and the relentless, often indifferent, march of the expanding universe. And what about the concept of extra dimensions for centuries? We have lived our lives firmly embedded in three spatial dimensions: up, down, left, right, and forward, backward. These are the dimensions we intuitively navigate, the very framework of our perception. But some profound theories, like string theory and M theory, gently propose the existence of additional spatial dimensions, tiny, curled-up dimensions that are too small for us to perceive. Imagine a garden hose viewed from afar. It looks like a one-dimensional line, but if you get closer, you see that it's actually a two-dimensional cylinder, with a tiny, curled-up dimension wrapping around it. Similarly, our universe might have tiny, compactified extra dimensions, hidden from our macroscopic view, yet influencing the very fabric of reality at the smallest scales. These extra dimensions are not just mathematical curiosities. They offer tantalizing solutions to some of the deepest puzzles in physics, such as why gravity is so much weaker than other fundamental forces. In some models, known as brain world models, our entire universe, all of its matter and energy, might be confined to a three-dimensional brain that floats within a higher dimensional bulk space, gravity. However, unlike other forces, might be able to leak into these extra dimensions, which would explain its comparative weakness in our perceived three dimensions. Imagine our universe as a sheet of paper, floating in a much larger, multi-dimensional room. Our lives are confined to the paper, but gravity can subtly extend into the wider room, diluting its strength within our two-dimensional world. It's a truly mind-bending concept, inviting us to reconsider the very boundaries of our existence and the hidden complexities of space. So, as we gently ponder these profound ideas, we realize that space is far from merely an empty void. It is a dynamic, elastic, and perhaps even multi-dimensional entity, deeply interwoven with time, gravity, and the very fabric of existence. It is not just where things happen. It is an active participant in how they happen. The more we delve into its mysteries, the more we realize the breathtaking complexity and elegance of the universe we inhabit. Consider for a moment the profound stillness that comes with truly contemplating these concepts. The idea of space expanding, curving, perhaps even vibrating with unseen dimensions. It can evoke a sense of immense peace, a quiet humility in the face of such grandeur. Our individual worries, our daily routines, seem to recede, don't they, when set against the backdrop of an expanding, dynamic cosmos. It's a reminder of our fleeting presence, yet also of our profound connection to this boundless living universe. And in that quiet connection, we might find a new appreciation for the space around us, even the seemingly mundane space of our everyday lives. The room you are in, the air you breathe, the ground beneath your feet, all are part of this grand, magnificent fabric of space-time. They are not merely empty gaps. They are expressions of this fundamental entity, shaped by the gentle pull of Earth's gravity, permeated by the subtle influences of the sun and distant stars. Every breath you take is filled with cosmic particles. Every glance you cast is through a space that is subtly curved and expanding. This contemplative journey into the nature of space is not meant to provide definitive answers, for many of these concepts are still at the very forefront of scientific inquiry, realms of profound mystery and ongoing exploration. Instead, it is an invitation to allow your mind to stretch, to expand, just as space itself does, and to embrace the beauty of not knowing, the wonder of simply asking. The universe, in its gentle wisdom, often reveals its deepest truths not through definitive pronouncements, but through whispered questions, inviting us to participate in its endless dance of discovery. As you lie here or sit or simply rest, imagine the quiet, intricate dance of particles within the very space around you, even in what appears to be empty air. Countless atoms and molecules are zipping, colliding, vibrating, creating a microscopic, silent symphony of activity. And beyond that, at even smaller scales, the quantum foam, the fundamental grains of space-time, are subtly fluctuating, bubbling with potential, a cosmic hum that is too faint for our ordinary senses to perceive, yet is nonetheless a part of the vibrant tapestry of reality. The silence of space, therefore, is not a dead, barren void. It is a teeming, dynamic, and profoundly active entity, far more intricate and alive than our initial perceptions might suggest. It holds the secrets of gravity, the whispers of expansion, and perhaps the hidden dimensions that shape our very existence. It is a mystery that continues to beckon, inviting us to delve deeper, to question further, and to simply marvel at the boundless beauty of its existence. The universe, it seems, is a master of paradox, offering us a concept that is both utterly familiar and endlessly alien. A constant reminder of the boundless wonders that lie just beyond the veil of our everyday perception. As we continue our gentle journey through the cosmos, allowing our minds to drift across the vast, intricate tapestry of space and time, our thoughts might now softly turn to one of the most fundamental and awe-inspiring events in the universe's grand narrative, the Big Bang. You've surely heard this phrase before, haven't you? It's the grand cosmic story of creation. The moment, perhaps, when everything we know and perceive came into being. But what does it truly mean to contemplate such an immense, almost incomprehensible origin? Imagine, if you will, not an explosion in the conventional sense, a chaotic burst of matter into existing space. No, the Big Bang was something far more profound, far more encompassing. It was the expansion of space itself from an infinitely hot, infinitely dense point. Before this moment, according to our current understanding, there was no before, because time itself began at the Big Bang. There was no outside for it to explode into, because space itself began to stretch and unfurl at that very instant. It's a concept that gently challenges our intuition, our deeply ingrained notions of cause and effect, of beginnings and endings. Think of it as the universe emerging from a single, unimaginably compact seed, smaller than an atom, yet containing all the potential for everything that would ever exist. And then, in a blink of what might be called cosmic time, this tiny seed began to expand, to swell, carrying all of space and time along with it. This was not a bang in space, but the very first moment of space and time and energy and matter. It's a truly humbling thought, isn't it, to consider such an ultimate beginning. Our current understanding, our best scientific model for this cosmic genesis, suggests that the Big Bang occurred approximately 13.8 billion years ago. Let that number settle softly in your mind. 13.8 billion years. It's an immense span, far beyond human comprehension. Yet, it represents the age of everything we can observe, the entire history of the universe unfolding from that initial, fiery singularity. For those first fleeting moments, the universe was an unimaginably hot, dense plasma, a soup of fundamental particles, so energetic that light could not even travel freely. It was a chaotic, brilliant cauldron of pure energy. But as space continued its rapid expansion, it began to cool, ever so slightly, ever so gently. And as it cooled, the fundamental forces of nature, which were once unified, began to separate out. Imagine a single, undifferentiated force, slowly splitting into the four distinct forces we recognize today: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. This was a profound moment of differentiation, a cosmic unfolding that allowed the universe to become the structured, intricate place we see. Then, at about 380,000 years after the Big Bang, something truly remarkable happened, a moment of profound transparency. The universe had cooled enough for electrons to combine with atomic nuclei, forming the very first neutral atoms, primarily hydrogen and helium. Before this moment, the universe was opaque, filled with a dense fog of charged particles. But once these first atoms formed, light was finally free to travel through space, unhindered. This ancient light, this fossil radiation, is what we now detect as the cosmic microwave background CMB radiation. It's the gentle whispering echo of the Big Bang, the oldest light in the universe, a profound message from the very dawn of creation, carrying within its subtle ripples the seeds of all future structures. When you listen to the CMB, you are literally listening to the universe's baby picture, a faint universal hum that tells us how smooth and uniform the early universe was, yet also how tiny, primordial fluctuations eventually grew into galaxies and clusters. The discovery of the CMB in 1964 was a monumental triumph for the Big Bang theory. It provided compelling observational evidence for a hot, dense, early universe, a silent yet undeniable confirmation of its fiery beginning. Imagine the awe of the scientists who first accidentally detected this pervasive background hum, realizing they were listening to the afterglow of creation itself. It was a profound moment of connection to the universe's deepest past. But of course, with such a grand story, deep questions naturally arise, don't they? One of the most perplexing is what came before the Big Bang. Our current theories of physics largely break down at the singularity, that infinitely dense point from which everything emerged. It's like reaching the edge of a map where the known territories end. The question, what was before, almost loses its meaning if time itself began at that moment. However, the human mind, in its boundless curiosity, cannot help but ask. This leads us to the realm of speculative theories, the quiet whispers of possibilities that attempt to extend our understanding beyond the Big Bang. One such idea is the inflationary universe theory. This theory proposes that in the merest fraction of a second after the Big Bang, perhaps from 10 Dors to 36 to 10 Dors to 32 seconds, the universe underwent an incredibly rapid exponential expansion. Imagine the universe suddenly inflating like a balloon blowing up at an unimaginable speed, far faster than its current expansion. This brief, powerful inflationary period could elegantly explain several puzzles of the standard Big Bang model, such as why the universe appears so flat and uniform on large scales, and why it's so incredibly smooth. It's like taking a tiny, wrinkled piece of paper and suddenly blowing it up to an immense size. The wrinkles would become imperceptibly small, giving the appearance of flatness and uniformity. Inflation provides a beautiful, albeit theoretical, explanation for these observed properties. A quiet, swift burst of expansion that smoothed out the primordial chaos. Another fascinating concept that attempts to address the before question is cyclic universe models, which we touched upon briefly when discussing time. These theories suggest that our universe is not a singular event, but one in an endless series of expansions and contractions, big bangs followed by big crunches, an eternal cosmic loop. Imagine a vast cosmic breath, inhaling and exhaling through eternity, each exhale giving birth to a new universe. In such a scenario, time would not have a beginning or an end, but would simply recur endlessly through cosmic epochs. The Big Bang, in this view, is merely a bounce, a moment of rebirth from a previous universe that contracted back into a dense state. It offers a cyclical, almost comforting sense of cosmic immortality. Then there are theories that delve even deeper into the realm of quantum cosmology, attempting to apply the principles of quantum mechanics to the entire universe, even to its very earliest moments. One such profound idea is Hawking's no-boundary proposal, developed by Stephen Hawking and James Hartle. This proposal suggests that the universe has no boundary conditions in space-time, meaning it did not have a specific starting point in time or space, like a Big Bang singularity. Instead, the universe, at its very earliest moments, was more akin to the South Pole on Earth. Imagine walking south on Earth. You always move south, but you never reach a boundary or a starting point from which to move south. Similarly, in the no-boundary proposal, space-time might curve around at the beginning, like the tip of a sphere, so that there is no initial singularity. This implies that asking what happened before the Big Bang is like asking what is south of the South Pole. The question simply loses its meaning. It's a concept that beautifully tries to unify the quantum world with the grand scale of the universe, suggesting a self-contained, elegant origin without a distinct start. And what about the idea of the multiverse? This concept, while highly speculative, gently suggests that our universe is just one among an infinite or vast number of other universes, each with its own Big Bang, its own set of physical laws, its own unfolding history. Imagine an endless cosmic foam where each bubble is a distinct universe, constantly budding off from others or arising from a larger, underlying reality. The inflationary universe theory, for example, can naturally lead to a multiverse, where different regions of the rapidly expanding space-time stop inflating at different times, each forming a separate bubble universe. In this view, our Big Bang is simply one bubble in an infinitely frothing cosmic ocean. The multiverse concept, while awe-inspiring, also touches upon the profound fine-tuning problem. We observe that the fundamental constants of physics in our universe, the strength of gravity, the mass of electrons, the speed of light, appear to be incredibly finely tuned for the existence of life. Even a tiny deviation in these constants would have resulted in a universe utterly inhospitable to stars, galaxies, or indeed, life itself. Why are these constants so perfectly just right? The multiverse offers a potential, albeit philosophical, answer. If there are an infinite number of universes, each with slightly different physical laws, then it is no surprise that we find ourselves in one that is perfectly tuned for life. It's like winning a lottery where every possible ticket combination is played across countless other universes. This perspective, while intriguing, is often debated, as it is inherently difficult to test scientifically. So, as we gently ponder the Big Bang and its profound implications, we realize that it is not merely a single event in the distant past. It is the very origin of space, time, and everything within them. It is a moment of cosmic genesis, shrouded in mystery, yet illuminated by the brilliant light of scientific inquiry. The more we learn, the more we realize the breathtaking elegance and complexity of our universe's beginning. The beauty of these theories, from inflation to cyclic models to the multiverse, lies not in their definitive answers, but in their capacity to expand our imagination, to push the boundaries of our understanding, and to invite us into a deeper, more profound appreciation for the sheer wonder of existence. They remind us that the universe is far more intricate, far more paradoxical, and far more awe-inspiring than we could ever fully comprehend. And as you lie here, allowing these grand cosmic narratives to gently unfold in your mind, you might feel a deep sense of connection to this vast, ancient story. You are, after all, made of stardust, the very elements forged in the hearts of long-dead stars, scattered across billions of years to coalesce into the complex being that you are. Your existence is a direct continuation of that initial fiery breath of the Big Bang, a testament to the universe's ceaseless creativity and its enduring ability to bring order from primordial chaos. The Big Bang is not just a scientific theory. It is a profound narrative of cosmic evolution, a story of how the very fabric of reality came into being. It is a reminder that we are part of something infinitely larger than ourselves, participants in a grand ongoing cosmic journey. And in that realization, there can be a profound sense of peace, a quiet acceptance of our place within the boundless, ever-unfolding universe. Allow your thoughts to drift now, carried by the gentle echoes of the cosmic microwave background, the oldest whispers of creation. Imagine the vast stretches of time that have passed since that initial, unimaginable moment, the countless stars that have been born and died, the countless galaxies that have formed and drifted apart. And in that immense sweep of cosmic history, your own existence is a tiny, precious flicker, yet connected to the very core of that grand beginning. This contemplation of the Big Bang is not meant to be a demanding intellectual exercise. Instead, let it be a soothing lullaby, a cosmic bedtime story that gently rocks your mind into a state of deep relaxation. There's no need to grasp every detail, no pressure to understand every nuance. Simply allow the grandness of the idea, the sheer scale of cosmic creation, to wash over you, like a gentle wave on a calm shore. It is a story of ultimate beginnings, a testament to the universe's capacity for constant, profound renewal. The universe, in its boundless wisdom, began with an unimaginable burst of energy and has been expanding, cooling, and evolving ever since. And within that vast ongoing process, we find ourselves tiny yet profoundly connected, pondering its mysteries. The Big Bang, therefore, is not just a scientific concept. It is an invitation to awe, a doorway to humility, and a gentle reminder of the endless wonders that unfold around us, even in the quietest moments of reflection. Let these thoughts carry you further into peace, into stillness, as the cosmic story continues its gentle, eternal telling. As we gently drift from the grand fiery dawn of the Big Bang, our thoughts might now softly settle upon a concept that, while seemingly intangible, holds immense sway over the very structure and fate of the universe, dark energy, and dark matter. You've probably heard these mysterious terms whispered in cosmic conversations, haven't you? They represent some of the deepest, most perplexing puzzles in modern cosmology, unseen forces and substances that quietly dominate the universe, yet remain stubbornly hidden from our direct gaze. Imagine, if you will, looking out at the vast tapestry of the night sky, filled with billions upon billions of glittering stars, swirling galaxies, and radiant nebulae. Everything you can see, everything that emits light, everything that interacts with our telescopes, all of that familiar, luminous matter makes up only a tiny fraction of the universe's total mass and energy. It's like looking at the tip of an immense, submerged iceberg, with the vast majority hidden beneath the cosmic surface. For decades, scientists observed the universe, carefully measuring the movements of galaxies and clusters of galaxies. They expected that, based on the amount of visible matter they could detect. These structures should be slowly decelerating, their expansion slowing down due to the mutual gravitational pull of all the matter within them. It's like throwing a ball into the air. Gravity should eventually pull it back down, slowing its ascent. However, the universe, in its gentle, surprising way, began to tell a different story. The first hints of the unseen came from the quiet observations of galaxies. In the 1930s, an astronomer named Fritz Zwicky, while studying the Coma cluster of galaxies, noticed something profoundly peculiar. The galaxies within the cluster were moving far too fast for the cluster to remain gravitationally bound based on the amount of visible light it emitted. It was as if a carousel was spinning so quickly that its riders should have been flung off, yet they remained firmly attached. Zwicky, with remarkable foresight, proposed that there must be some unseen, non-luminous matter providing the extra gravitational glue to hold the cluster together. He called this mysterious substance dark matter. His whispers were largely ignored at the time, too radical for the prevailing views. Decades later, in the 1970s, the concept of dark matter gained much stronger footing through the meticulous work of Vera Rubin and her colleagues, who studied the rotation curves of spiral galaxies. Imagine a spinning galaxy, like a cosmic pinwheel. You would expect the stars and gas at the outer edges to orbit more slowly than those closer to the center, just as planets further from a star orbit more slowly. However, Rubin found that stars at the outer edges of galaxies were rotating just as fast as those closer to the center, or even faster. This defied the gravitational expectations based on visible matter alone. It was as if a figure skater was spinning, but her arms, instead of slowing down as they extended, maintained the same speed as her core. The only explanation was that there must be a vast, invisible halo of matter surrounding these galaxies, extending far beyond the visible stars, providing the extra gravitational pull to keep the outer regions spinning so quickly. This unseen substance, too, was identified as dark matter. So, what is this dark matter? We know, with remarkable certainty, that it must exist, because its gravitational effects are clearly observable on cosmic scales. Galaxies spin faster than they should. Galaxy clusters hold together despite the high velocities of their member galaxies. Gravitational lensing, where the immense gravity of massive objects bends light from background galaxies, reveals far more mass than can be accounted for by visible matter. This unseen mass acts as the gravitational scaffolding upon which the visible universe is built, gently holding galaxies and clusters together. However, despite its pervasive influence, dark matter is truly dark. It does not emit, absorb, or reflect light or any other form of electromagnetic radiation. It doesn't interact with the fundamental forces of electromagnetism or the strong and weak nuclear forces, which govern the interactions of ordinary matter. The only way we currently know it interacts is through gravity, This means we cannot see it, touch it, or directly detect it with any of our current instruments. Imagine a ghost, passing silently through everything, its presence only betrayed by the subtle effects it has on the things it passes near. This profound elusiveness is one of its most captivating mysteries. What is dark matter made of? This remains one of the greatest unanswered questions in physics and cosmology. The ordinary matter that makes up stars, planets, and us, protons, neutrons, electrons, is called baryonic matter. But dark matter is clearly not baryonic. If it were, we would detect its presence through its interactions with light or other forces. Instead, scientists hypothesize that dark matter is composed of entirely new, exotic particles that interact only very weakly with ordinary matter, primarily through gravity. These hypothetical particles have been given various names like WIMPs, weakly interacting massive particles, or even axions. Experiments deep underground, shielded from cosmic rays, are constantly trying to detect these elusive particles, hoping for a tiny, fleeting interaction that might finally reveal their true nature. The search is a testament to human patience and ingenuity, gently listening for the quietest whispers of the unseen. And then, just as scientists were grappling with the enigma of dark matter, the universe unveiled an even more astonishing secret: dark energy. This discovery emerged in the late 1990s from independent observations of distant type Ia supernovae. These specific types of exploding stars are known as standard candles because they always explode with a consistent peak brightness. By measuring how bright they appear from Earth, astronomers can calculate their distance, and by measuring their redshift, they can determine how fast they are moving away from us due to the expansion of the universe. The expectation was that the expansion of the universe, driven by the initial impetus of the Big Bang, should be gradually slowing down due to the gravitational pull of all the matter both visible and dark within it. But the supernova observations revealed a breathtakingly unexpected truth. The most distant supernova were fainter than expected, meaning they were farther away than predicted for a decelerating universe. This implied that the universe's expansion was not slowing down, but was, in fact, accelerating. Imagine throwing that ball into the air, expecting it to slow down, but instead, it begins to speed up, flying away faster and faster. This was a truly profound, almost paradoxical revelation. To explain this accelerating expansion, cosmologists proposed the existence of a mysterious, pervasive force they named dark energy. Unlike dark matter, which acts like an invisible gravitational glue, dark energy appears to be a form of repulsive gravity, gently pushing space-time apart, driving the universe's expansion to accelerate. It's as if the very fabric of space itself has an inherent energy, a cosmological constant that pushes it outwards. Dark energy is even more enigmatic than dark matter. We don't know what it is, where it comes from, or why it exists. It accounts for approximately 68% of the total energy density of the universe, making it the single largest component of our cosmos. Combined with dark matter about 27%. This means that all the ordinary matter we can see and interact with, the stars, galaxies, planets, and ourselves, makes up only a tiny 5% of the entire universe. Imagine that. Everything we have ever known, everything we have ever studied, is just a whisper in the grand symphony of existence, with the vast majority of the universe composed of these invisible, mysterious entities. The most favored explanation for dark energy is the cosmological constant, a concept originally introduced by Einstein but later abandoned by him as his biggest blunder. This constant suggests that dark energy is an intrinsic property of space itself, meaning that as space expands, more dark energy is created, thus driving further acceleration. It's a self-perpetuating cosmic engine gently pushing the universe towards an ever faster expansion. Alternative theories for dark energy include quintessence, a hypothetical dynamic energy field that changes over time, or modifications to Einstein's theory of gravity on cosmic scales. But for now, these remain speculative whispers in the vast, echoing halls of theoretical physics. The universe, it seems, holds its deepest, most profound secrets close, challenging us to push the boundaries of our understanding. The existence of dark energy has profound implications for the ultimate fate of the universe. If it continues to dominate the universe's expansion, it could lead to scenarios like the Big Rip, where the accelerating expansion eventually tears apart galaxies, stars, and even atoms themselves, leaving a cold, empty, truly isolated universe. Or, in a slightly gentler scenario, the Big Freeze or heat death, where the universe expands indefinitely, becoming ever colder and more dilute, until all energy is uniformly distributed and no further processes can occur. These are sobering thoughts, aren't they? Contemplations of an ultimate cosmic stillness, a final, boundless silence. So, as we gently ponder these immense unseen components of our universe, dark matter and dark energy, we are left with a profound sense of awe and humility. They represent the vastness of our ignorance, the immense mysteries that still lie beyond our grasp. We know they are there because we observe their effects, their subtle yet undeniable influence on the cosmic dance. But their true nature remains shrouded in a captivating darkness, a silent beckoning for further exploration and deeper understanding. Imagine the universe now, not as just the stars you see, but as a colossal, invisible structure. Picture vast, intricate webs of dark matter spanning across cosmic distances, forming the skeletal framework upon which galaxies and galaxy clusters are built. And then, imagine an invisible, pervasive force, dark energy, silently pushing, gently accelerating the very fabric of this cosmic web, driving everything apart. It's a universe far more complex, far more dynamic, and far more mysterious than our visible senses can ever fully comprehend. This contemplation of the unseen, of the dark side of the cosmos, can be profoundly calming. It reminds us that our perception is limited, that there is always more to discover, always deeper layers of reality to uncover. It teaches us a gentle humility, a recognition that the universe holds secrets far grander than our immediate understanding. In the face of such immense hidden forces, our everyday worries seem to recede, don't they? They become small whispers against the backdrop of cosmic enigma. And as you lie here, allowing these ideas to gently float through your mind, you might feel a deeper connection to the mystery itself. You are a part of this universe, a tiny collection of ordinary matter, yet intricately linked to these unseen cosmic components, the very galaxies that formed and exist today, the stars that shine, the planets that orbit, all owe their existence and their behavior to the subtle influence of dark matter and dark energy. Your existence is woven into this grand, unseen tapestry. This journey into the dark corners of cosmology is not meant to create anxiety or a sense of insignificance. Rather, it is an invitation to embrace the unknown, to marvel at the profound beauty of what we don't yet understand. The very fact that these mysteries exist, that the universe continues to hold such fundamental secrets, is a testament to its boundless wonder and its unending capacity to surprise us. It keeps us curious, keeps us questioning, keeps us reaching for the limits of knowledge. Allow your mind to drift now, carried by the subtle currents of dark energy, guided by the unseen scaffolding of dark matter. Imagine a universe that is mostly invisible, mostly silent to our direct senses, yet profoundly active and dynamic beneath the surface. It is a universe that challenges our assumptions, expands our horizons, and invites us to contemplate the deepest questions about existence. Let these thoughts carry you further into peace, into stillness, as the cosmic story continues its gentle, eternal telling, even in its most mysterious chapters. As we gently float through the cosmos, having considered the unseen mysteries of dark matter and dark energy, our minds might now softly turn to an even more perplexing, yet perhaps more personally resonant, concept, the multiverse. You've probably heard this idea whispered in hushed tones, a tantalizing suggestion that our universe might not be the only one, but simply one bubble among an infinite sea of other universes. It's a thought that stretches the very fabric of our imagination, isn't it? Imagine, if you will, that our entire universe, with its billions of galaxies, its countless stars, and all the space and time we know, is just a single droplet in a vast, boundless ocean. Each droplet in this grand cosmic ocean is a complete universe in itself, with its own unique laws of physics, its own beginning, and its own unfolding destiny. This is the essence of the multiverse concept, a breathtaking expansion of our cosmic horizons. This idea, while seemingly fantastical, actually emerges quite naturally from some of our leading cosmological theories, particularly the inflationary universe theory we gently touched upon when discussing the Big Bang. Recall that brief, incredibly rapid period of exponential expansion that smoothed out our early universe. If this inflation went on forever, never truly stopping everywhere at once, it could lead to a scenario where different regions of this rapidly expanding space-time stop inflating at different times, or in different ways. Each of these stopped regions could then bud off, forming a separate, distinct bubble universe. Imagine a vast, ever-expanding foam, where each bubble is a new universe, constantly forming and drifting away from its siblings. In this eternal inflation scenario, our universe is simply one of these countless bubbles. Each bubble might have slightly different fundamental constants, different numbers of dimensions, or even entirely different sets of particles and forces. It's a cosmic lottery, where every possible combination of physical laws might be realized in some corner of this infinite foam. This particular version of the multiverse, derived from the mechanics of inflation, suggests an unending frothing creation of new realities. Another way to gently conceive of a multiverse comes from string theory and its more expansive cousin, M-theory. These theories, which propose that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings or membranes brains, naturally allow for the existence of extra-spatial dimensions. As we gently discussed before, these dimensions might be curled up too small for us to see. Or perhaps our entire universe is a three-dimensional brain floating in a higher dimensional bulk space, like a piece of paper in a large room. In the context of M-theory, the multiverse could arise from the collisions of these vast, multi-dimensional brains. Imagine two immense cosmic sheets, perhaps existing in a higher dimensional space, gently drifting towards each other. When they collide, the immense energy of the impact could create a new universe, a new Big Bang, sparking a new reality on one of the brains. This is the concept of a cyclic or colliding brain multiverse, where universes are born from the reverberations of previous cosmic encounters, perhaps leading to an endless cycle of creation and destruction. In this scenario, the Big Bang might not be the absolute beginning of everything, but merely a violent collision in a larger, multidimensional arena. Then there is the more abstract yet equally fascinating idea of the many worlds interpretation of quantum mechanics. This interpretation, while not directly related to the expansion of space, suggests that every time a quantum measurement is made, every time a probabilistic event occurs, The universe splits into multiple parallel universes, one for each possible outcome. Imagine a subatomic particle that can be in two states at once when you measure it, and it chooses one state. In the many worlds interpretation, another universe branches off where it chose the other state. This would mean that an infinite number of parallel realities are constantly branching off from our own, moment by moment, for every decision made, for every quantum fluctuation. It's a mind-boggling concept, suggesting an infinite multitude of yous, living out every conceivable alternative reality. While it addresses some paradoxes of quantum mechanics, it also presents a vast, almost overwhelming picture of cosmic redundancy. So, why do physicists even consider such an expansive, seemingly outlandish concept as the multiverse? The primary motivation is often to address profound questions and puzzles within our own universe that are otherwise difficult to explain. One of the most compelling reasons is the fine-tuning problem, which we briefly touched upon. As you may recall, the fundamental constants of physics in our universe, the precise strength of gravity, the exact mass of the electron, the speed of light, the strength of the nuclear forces appear to be incredibly finely tuned, almost miraculously so, for the existence of stars, galaxies, and ultimately, life itself. If any of these constants were even slightly different, the universe would be a barren, lifeless place. Imagine adjusting a delicate dial on a cosmic machine. If it's off by even a tiny fraction, the machine simply doesn't work. This seemingly miraculous fine-tuning leads to a profound question. Is it just an extraordinary coincidence, or is there a deeper explanation? The multiverse offers a potential, albeit philosophical, solution to this puzzle. If there are an infinite number of universes, each with slightly different fundamental constants, then it is no surprise that we find ourselves in one that is perfectly tuned for life. It's simply an inevitable outcome of probability. If you roll the dice an infinite number of times, eventually, you are bound to roll the exact combination you are looking for. In this view, our perfectly balanced universe is not a miracle, but simply a consequence of existing within an unimaginably vast cosmic ensemble. It is a quiet reassurance that somewhere out there, the conditions for life must exist. The implications of a multiverse are truly immense, stretching the very boundaries of our philosophical and scientific thought. If our universe is just one of many, it profoundly changes our perception of our place in the cosmos. We are no longer the singular, unique creation, but part of a grander, perhaps endless, cosmic tapestry. This realization can be both humbling and exhilarating. It reminds us of the vastness of existence, the boundless possibilities that might unfold beyond our own cosmic horizon. However, the concept of the multiverse also presents significant challenges, particularly in terms of scientific testability. How can we ever hope to detect or observe these other universes if they are, by their very nature, causally disconnected from our own? How can we gather empirical evidence for something that exists beyond our observable universe? This question lies at the heart of the debate surrounding the multiverse. For some, if a theory cannot, in principle, be tested or falsified, it begins to venture outside the realm of science and into the realm of philosophy or metaphysics. Yet, despite these challenges, the idea of the multiverse continues to captivate the minds of scientists and dreamers alike. It offers a powerful intellectual framework for pondering some of the deepest questions about existence. Why is there something rather than nothing? Why are the laws of physics what they are? Are there other intelligent beings out there, perhaps even infinite versions of ourselves, living out different cosmic narratives? The questions whisper, don't they, inviting us to delve into the realm of pure possibility. And as you lie here, allowing these grand, mind-bending concepts to gently unfold in your consciousness. You might find a strange, profound comfort in the idea of the multiverse. If there are infinite possibilities, then perhaps every potential outcome, every quiet longing, every unfulfilled dream is realized somewhere in some parallel reality. It's a thought that can bring a sense of cosmic acceptance, a gentle release from the weight of singular paths. Imagine the vastness of its universe is constantly budding, stretching, perhaps even colliding in dimensions beyond our wildest grasp. Some might be empty and cold, others teeming with exotic life forms, still others perhaps subtly different versions of our own, where history took a slightly different turn. The sheer scale of such a reality is almost too much for the human mind to fully comprehend. Yet it is precisely this boundless immensity that can be so soothing. Our individual existence, our tiny lives, become part of a grander, more infinite play, a boundless cosmic tapestry woven from countless realities. This exploration of the multiverse is not about finding definitive answers or proving grand theories. It is, instead, an invitation to quiet contemplation, to allow your mind to expand and stretch beyond the familiar boundaries of your own perceived reality. It is a gentle reminder that the universe, or perhaps the multiverses, hold secrets far more intricate and awe-inspiring than we can currently imagine. The very act of pondering such vast concepts can bring a sense of peaceful detachment, allowing the anxieties of the immediate world to recede, replaced by a quiet wonder at the sheer scale of existence. Allow your thoughts to drift now, carried by the subtle currents of cosmic possibility. Imagine your consciousness, a tiny spark, floating through an endless sea of universes, each a unique expression of reality. There is no urgency to grasp every detail, no pressure to understand every nuance of string theory or quantum mechanics. Simply allow the grandness of the idea, the sheer scale of cosmic abundance, to wash over you like a gentle, infinite wave. The multiverse, therefore, is not just a scientific hypothesis. It is a profound philosophical statement, an invitation to awe, a doorway to humility, and a gentle reminder of the endless wonders that unfold around us, even in the quietest moments of reflection. Let these thoughts carry you further into peace, into stillness, as the cosmic story continues its gentle, eternal telling in this universe, and perhaps in countless others. The very act of imagining such boundless possibilities can be a profound source of tranquility, a gentle reminder that our own tiny bubble of reality is merely one note in an infinite cosmic symphony. As our gentle journey through the cosmic tapestry approaches its quiet conclusion, having explored the vastness of Alpha Centauri, the enigmatic nature of time, the profound stillness of space, the fiery birth of the Big Bang, and the mysterious whispers of dark energy, dark matter, and the multiverse, our minds might now softly settle upon a concept that, while seemingly boundless, is perhaps the most personal and immediate the human mind itself, and its boundless capacity for curiosity and wonder. You are here, now, reading these words, experiencing this gentle journey, and in this very act, you are demonstrating one of the most remarkable phenomena in the known universe, the ability of consciousness to contemplate its own existence, to question the very fabric of reality, and to reach out into the vast, silent expanse of the cosmos with an unquenchable thirst for understanding. Where does this curiosity come from? This innate drive to know, to explore, to unravel the universe's deepest secrets. It is a mystery as profound as any celestial body, as enigmatic as any dark energy. Think for a moment about the incredible journey your mind has taken throughout these chapters. We have spoken of distances so vast they defy imagination, light years, trillions of kilometers. We have spoken of timescales so immense they humble our fleeting lives, billions of years, even trillions. We have spoken of forces unseen, substances undetectable, and realms beyond our direct perception. And yet, your mind, this intricate network of neurons and synapses, has effortlessly traversed these cosmic landscapes, absorbing concepts, forming images, and pondering implications. This capacity for abstract thought, for imaginative leaps, for boundless wonder, is truly a miracle, isn't it? The human mind, in its essence, is a miniature universe, mirroring the cosmos it seeks to understand. Just as the universe expanded from a point, your consciousness expands with every new piece of knowledge, every new question posed. Just as space warps around massive objects, your perception can be shaped and molded by experiences, by beliefs, by the very stories you tell yourself. And just as time flows, your thoughts move ceaselessly from memory to anticipation, from reflection to new insight. Our curiosity, this fundamental human trait, has been the driving force behind every scientific discovery, every philosophical inquiry, every artistic creation. It is the quiet spark that led ancient civilizations to map the stars, that propelled daring explorers across vast oceans, and that continues to push scientists to peer deeper into the atom and further into the cosmos. It is a restless, beautiful urge to connect, to comprehend, to find meaning in the seemingly chaotic dance of existence. But curiosity is not merely about accumulating fact. It is also about a profound sense of awe and wonder. When we contemplate the sheer scale of the universe, the elegance of its laws, the intricate dance of its particles, we are often struck by a feeling of profound humility, a quiet reverence for something far grander than ourselves. This feeling of awe is not a passive emotion. It is an active engagement with the sublime, an opening of the mind to possibilities that transcend our everyday understanding. It is a moment when the boundaries of self seem to dissolve, and we feel a deep, undeniable connection to the boundless cosmos. And in that connection, we find a sense of belonging, despite our physical smallness, our individual fleeting existence. The very act of understanding, of wondering, of contemplating the universe makes us an integral part of its story. We are not merely observers, we are participants, living expressions of the universe's capacity to reflect upon itself. The elements that make up your body were forged in the hearts of distant stars, scattered across cosmic eons, and gathered here on this living planet to awaken into consciousness. You are literally stardust, contemplating starlight. What a magnificent thought, isn't it? Yet for all its power, the human mind also possesses a remarkable capacity for stillness and peace. In our fast-paced world, filled with constant stimulation and endless demands, finding moments of tranquility can feel like a challenge. But it is precisely in these quiet moments that our minds can truly expand, truly wander, truly connect with the deeper rhythms of existence. When you allow your thoughts to drift, unburdened by urgency, when you simply listen to the gentle whispers of the cosmos, you are engaging in a profound act of self-care, a quiet pilgrimage into the inner sanctuary of your being. This journey through scientific concepts, presented in a gentle, calming way, is an invitation to cultivate that stillness. It is a reminder that the pursuit of knowledge doesn't always have to be a race. It can be a slow, meditative stroll through the grand corridors of cosmic understanding. There is no exam to pass, no answer to memorize, only the profound beauty of contemplating vast ideas, allowing them to wash over you like gentle waves on a serene shore. Consider the act of imagination when we speak of black holes, of warped space-time, of universes branching off. You conjure images in your mind, don't you? You visualize concepts that have never been directly seen, that exist purely in the realm of theory and mathematical elegance. This creative capacity, this ability to build entire realities within the confines of your skull, is another testament to the mind's extraordinary power. It is this very power that allows us to dream of interstellar travel, to envision Earth 2.0s, and to search for answers to questions that have plagued humanity for millennia. But perhaps the most beautiful aspect of our mind's journey into the universe is its embrace of uncertainty. In science, we rarely have all the answers. We have theories, models, hypotheses, elegant frameworks that explain what we observe, but which are always open to revision, always subject to new evidence. The existence of dark matter and dark energy, the true nature of time, the ultimate fate of the universe, these remain profound mysteries, questions that continue to beckon us into the unknown. And in that not knowing, there is a deep, liberating peace. It frees us from the pressure of needing to have all the answers, of needing to define everything. Instead, it invites us to live in the realm of possibility, to embrace the ongoing journey of discovery, to find beauty in the very questions themselves. The universe, in its boundless mystery, is always offering us new puzzles, new wonders, new invitations to explore the limits of our understanding, and the human mind, in its boundless curiosity, is perfectly equipped to accept that invitation, to embark on an endless journey of quiet contemplation and profound discovery. So, as we bring this final chapter to a gentle close, let us not seek a definitive conclusion to our cosmic wandering, for the universe, and the human mind that contemplates it, are realms of infinite exploration. Instead, let us simply rest in the quiet beauty of the ideas we have explored together. Let the vastness of space, the flow of time, the echoes of the Big Bang, the whispers of the unseen, and the boundless possibilities of the multiverse gently settle within your consciousness. Feel the profound peace that comes from simply being, from simply allowing your mind to wander without agenda, without expectation. There is no urgency here, no demand for action, only the quiet hum of existence, the gentle rhythm of your breath, and the endless tapestry of cosmic wonder stretching out before you. This is not a final destination, but merely a pause in a much larger, ongoing journey of curiosity. The universe will continue to unfold its secrets, and your mind will continue to seek them, drawn by that inherent wonder that defines us. So, as the last words gently fade, let yourself drift, carried by the profound peace of knowing that you are part of something magnificent, something infinitely mysterious, something truly beautiful.